Tamam mıyım? Ses duyuluyor. Tamam. Buyur. Tamam. Nasıl sunulacak? Yani siz nasıl? Türkçe biraz garip olur. İngilizce şey yapmak doğru. Bir dakika. Dil görünmüyor. Evet. Share screen var. Ha, interpretation. Ha, evet. Türkçeyi. Tamam. Evet. Tamam. Tamam. Tamam oldu. Teşekkür ederim. Görüntümü kapatıyorum. Şu anda sigara içiyorum çünkü. Kapatıyorum. Tamam, hadi bay bay.
Değerli katılımcılar, salonumuza hoş geldiniz. Toplantı başlamadan önce Zoom'daki Interpretation alanından konuşacağınız dile göre lütfen seçiminizi yapınız. Her sunumun süresi 15 dakikadır. Sonrasındaki 5 dakika oylama ve temenni süresidir. Oylama linki sunumun bitişinde chat üzerinden paylaşılacaktır. İyi toplantılar diliyorum. Dear participants, welcome to the meeting. Before starting, please choose English on interpretation menu in Zoom. Every presentation has 15 minutes to complete. After that, you have 5 minutes to vote and share opinions. The link for voting is shared on chat at the end of the presentation. Wish you a good meeting.
Teşekkür ederiz Eda Hanım. Sayın Genel Müdürlerim, sayın hocalarım, kıymetli araştırmacılar ve değerli misafirler, 3. Bioenerji Çalışmaları Sempozyumuna hoş geldiniz. Birinci oturuma başkanlık yapması için Sayın Profesör
Teşekkürler Hüseyin Bey. İzmir'den tüm katılımcıları saygıyla selamlıyorum. Bu oturumumuzda sunumlar genel esas olarak biyogaz üretimiyle ilgili. İlk konuşmacımız Doktor Figen Ar. Sunumunun başlığı Empowering an Emerging Market with Biogas, the Case of
Thank you very much. I want to turn my camera on. Could you please? I think I don't have this authority to do this. Now,
bir kez daha hatırlatayım isterseniz. 15 dakika konuşma süresi, 5 dakikada tartışma.
let me share the research which we have conducted, and we will be looking at the biogas market. We will have a question and answer session too. Why we have conducted this study? Because in the developed and developing countries, there is a difference in the efficiency. We wanted to put forward and reveal these differences, and also we wanted to make a literature review. because we wanted to reveal the inconsistency between developing and developed countries, because there is a need for improvement in the developing market in Turkey. Our motivation for the study was the following: to create value in biogas sectors in Turkey and in developed countries, and to reveal the differences. And our goals were the capturing the current discrepancies among Turkey and advanced countries in terms of biogas production process and usage. And this will be showing the importance of the study. Here, developing and developed or emerging versus advanced countries can be defined, because we need to define it. These are internationally accepted definitions. Emerging markets or developing countries, as the speaker used in Turkish, are the countries that already surpassed the developing economy stages about to reach the advanced economy phase. They have the ability to produce high added value products in all industries. And these are called EM7 countries, including Turkey. And other countries are Brazil, China, Turkey, Russia, India, Mexico, and Indonesia. And also we have a definition for the advanced country. And in this definition, which are the countries leading the GDP output of the countries. They are resilient against the crisis, and they are stable countries. The most best known countries are these are the countries which you see: Canada, Germany, Italy, and other countries. And this is also overlapping with the classification of London Stock Exchange. You see Turkey is among the developing countries. This is the list of the stock exchange. There are millions of biogas activities, and 48 millions are in China and India, but they are working with primitive methods. There are 265 biomass plants in America based on wastes, and it is producing around $1 billion. I have to interrupt the interpretation. Sorry for the interruption, there was a technical problem. Now we are going on. And in Germany, you can see the figures which is applicable. And another output of the sector is 19.9 million tons of CO2 saving. Because methane is very effective, 27 times more, having a more negative impact on climate change. That's why biogas is very important. It's not only to produce related to dealing with the waste, but also it is an important parameter in climate change, and it's a sector which we want to change. India, Minister of Oil and Natural Gas in 6th of February 2019 made a statement saying that they would be setting up 5,000 new biogas plants. As you see, there are important progress in emerging markets too, and developed countries are already leading the sector. You see the figures of 3 developed countries, economic and technical figures. Germany data for the biogas generation or production per capita, and in Turkey we have a problem with this regard too. As you see, sector is very important, and economic data is being kept year by year, and its contribution in economy is being determined, and there are policies developed in this vein, and the impact is increasing. This is a very recent study in 2021. You can see the details, and in these graphics are belonging to 2021 years. You see the advanced country sample data. Germany, as you see, beginning from 2010, is continuing to produce biogas, increasing year by year. Beginning from 2018, biomethane is being produced too. You see 160 methane and 60% CO2. This is the mixture of biogas. But when you take out CO2 from biogas, you have a pure natural gas, because natural gas is 96% methane and 4% ethane, butane, and other gases. But 96% is methane. So if you can upgrade the carbon, upgrade the biogas by taking out the CO2, you are obtaining a natural gas through biological means. And this is not only possible to use in electricity generation, but in any area where you can use natural gas. For example, you can use it in bus fuels. As a bus fuel, it's very widespread. Beginning from 1994, in Lycan, France, the buses are using biogas. In the same way, in Germany, in the United States of America, you can see the examples. Not only developed countries, but also developing countries, the emerging markets are using this. For example, in Malaysia, in India, there are buses which are using biogas. Not only buses, but also you can use biogas in any field where you use natural gas, not only for electricity and heat generation, but also you can use it to produce fuel. And trains are using this. Also in Formula One, in one Formula One race, biogas was used. This is a photo of a biogas bus. There is a drawing and there is the real picture. It is working with yearly waste 5 people. It's a bus working with only with the biogas produced with the waste of 5 individuals. What about in our country? In our country too, we have biogas plants. Actually, it is apple of our eye because it's so valuable. For example, you see a Sütaş, a dairy product, dairy factory plants. They have in Aksaray, plants in Aksaray and Bursa. One is 2.4 megawatt, other one is 4.6 megawatt. And the other plant is in Gönen, Altaca. Now it has a new owner, Toros Fertilizer Producers, took over the plant. And in both plants, the wastes are being used, especially in Gönen. Fermented waste is used also as organic fertilizer. Is it enough? No. Just we can say, as Turkey, we are producing electricity and heat from biogas plants. Unfortunately, we can only use electricity, and we don't make a sufficiently efficient use of heat. So we have both efficiency and diversity at stake. I hope I could make a distinction between biogas and methane. Biogas is 60% methane and 40% CO2, but biomethane is pure methane. In other words, pure natural gas. Unfortunately, in our country, we don't have biomethane plants. 12 years ago, I have visited Germany, and I visited a 10 megawatt biomethane plant. Since then, I really want to have a comparable plant in our country. So far, we don't have it. I know that there are studies. In our country, we don't have a distinction in data collection related to biogas plants. Energy Market Regulatory Board is collecting the data, but they are being collected under the umbrella of biomass. You know, when we speak about biomass, of course, there are gas and other. You have only 1 minute. Could you please wrap it up? You see, it has a low capacity. It's not efficient, and unfortunately, we don't have a very nice picture in Turkey with regards to efficiency or diversity. Sorry. In conclusion, when we make a comparison between emerging markets and advanced countries value creation is well over the values created by emerging markets based on US dollars. But also, there are differences among the emerging markets. Turkey, when compared within EM7 countries, biogas is only used for electricity and heat production. It can be used in transport. It can be used in any branch of industry. And it has a huge potential to do this. Also, biogas sector is very important with regards to employment, circular economy, and combating climate crisis. And it is a priority sector in combating climate sector, which is also revealed by the International Energy Agency. Thank you very much for your patience.
Thank you so much for this interesting talk. I'm checking the questions, but I think there is no question yet. Again, I just want to ask you a question. I'm not a biogas expert, but as far as I heard, if you look at the biogas facilities and for their feasibility, we need a certain capacity beyond a certain level You just can't, identify or assign a biogas facility anywhere else. Yes, you're exactly right, because biogas facilities are also biochemical facilities. There are bacteria involved. You have to create the environment for such bacteria, the required pH level, temperature, mixture level, and carbon nitrogen ratio. In small systems like villages or individual systems, it will be extremely impossible to get all those requirements right, which will bring you a security problem, a pathogen problem. For this reason, both on economical terms and also for sustainability and safety, yes, it wouldn't be very feasible under a certain level or capacity. Thank you so much. A second biogas expert, Nuri, raises hand, so I would like to give him the floor. Nuri, the floor is yours. Hello, first of all, everyone. Figen, I'm also very glad to see you once again. It's a very timely presentation. I would like to thank you so much for this great talk. In Turkey, biogas was about to flourish in Turkey, but it was limited to only 63 facilities. And I believe with these incentives, I think no other investment will be involved in this area. But maybe we can turn this into an advantage, because as you also rightfully said, as you know, there's also the green agreement, and there are certain requirements. Also, we see examples in Europe too. We held an international workshop in Izmir, and the use of mud in public transport, and we selected this title intentionally because we wanted people to understand the issue. But we understood that the problem is not technical. Like, the decision makers think about this as an utopia. They don't think that it's feasible. They see it only like a dream. But we know that there are certain biogas facilities that have received incentives for 10 years, but we need to bring about something like biomethane, and because it's also very advantageous, but at the purification side, the cost is also increasing. So that's why we don't have the legislative part ready either. The biogas use in transportation, I don't know how it's going to happen, but I just want to send out a message to the decision makers that we need a regulation as soon as possible so that biogas is commonly used. Thank you very much for giving the floor. I would like to thank you so much for your contribution. You're right, and I agree with you. Thank you very much for the comments. Now we switch to the second speaker, Nuri, Professor Dr. Nuri Asbar. He's also from the Aegean part of Turkey, and he will be talking about effect of various thermal chemical pretreatment on biomethanization of hemp herd and kinetic analysis. Let me share my presentation and turn on my camera. Can you see me? Yes, we can see your slide. Distinguished participants and chairpersons, I would like to welcome you all, and I would like to thank everyone for this great organization. And we have really valuable speakers, and we touch upon really important subjects. In EGE University, we work with Jale very closely, and we have tried a lot of biomasses. It is not only limited to one or two materials, but there are so many alternative biogas materials that we have tried. As you also know, there is a plant which is Cannabis sativa, becoming very popular lately, and under the coordination of the ministry, it has been permitted to be grown in certain provinces because it also has other advantages in medicine as well. And in the meanwhile, also we have a stakeholder from the Ministry of Agriculture and Forestry, the Black Sea Agricultural Research Institute. So first of all, I would like to also thank them for their participation in this project. You all know hemp, so we don't need to talk about it in detail. Of course, there are unfortunately illegal uses of this plant, but there are thousands of researchers and studies showing the benefits of hemp, and it's like the Swiss knife. You know, there are so many advantages and benefits of this plant, from pharmaceuticals to cosmetics, especially THC and CBD molecules play an important role, especially in the treatment of cancer with proven studies. So basically, this plant has numerous benefits, especially we know that the leaves uh, have been also the subject of many studies with respect to biogas studies. In this study, we try to show the real benefit uh, of of the stuff. There is a cellulosic area in the body of the plant. So we wanted to understand if we could use this structure, the hemp heart especially, which is the woody interior part of the hemp stems. So this is basically used in the paper industry or building materials. So we wanted to understand if we could use this as a biomass. When you look at the volatile raw material, if it is a biologically accessible material, then you can use different fermentation and different processes. And of course, we talk about the anaerobic uh, processes. So we wanted to see whether we can use it as a hydrogen. But like there are also biofuels like bioethanol or biobutanol. They can be also used as liquid um, fuels in many countries. We see it, especially in Germany, as Figen also pointed out. It's a leading country, by the way. I think there are around 9,300 biogas facilities in Germany. So basically, Germany is really a good example and pioneer for different countries. And they also have plans of investments in Turkey because Turkey has a really big potential. With regards to cannabis, of course, uh, there are certain parts that really have an important added value. So in this study, we wanted to show whether we can use it. The hemp heart, what we call, is a hemp heart. It looks like the wood scrap, and of course, it cannot be broken down by bacteria easily. That's why we need certain preliminary processes that will enable the bacteria to break down the hemp heart. Uh, our study consists of 8 packages indeed, but we just wanted to show you just one side of this study, especially with regards to, as I will be talking about in my afternoon talk, dry fermentation is an important process, and it's really, really good for the hemp herd. I cannot show you it right now in this presentation, but I will just try to show you the biogas improvement potential with regards to this hemp herd. What we did here is basically the ministry sent us two different varieties of cannabis hemp herds, and they harvested them and they sent them to us, and I would like to thank the ministry once again for this. So we took these two varieties, and let me show you like this. As you can see, there was a really wide matrix of pre-treatment. As you can see on the left, this is a hemp herd which cannot be used directly, so we had to grind them to bring it down to a certain level so that it can be used. And we did all the pre-treatment, but of course we needed a witness sample which was not pre-treated, so there's also this witness material as well. And this was followed by, of course, the most widely used processes like alkali, acid, thermal. You can also combine them with acid and thermal, or alkali and thermal, and then pre-treat them, and then switch to BMP process. Probably you all know about the BMP. This is the potential for the biomethane production, and it is the single and the most valuable test for us to see how much methane a material can produce. Very simply put here, you can see, of course, we have the fully automated systems, but I just wanted to show you the preparation of BMP. You have the substrate and the anaerobic seed combined with the sample. Of course, you have certain micronutrients and water, and then the headspace with the sealed bottle. And in this way, we try to see, of course, the gas production and the methane production. And then the system calculates this all, and then we try to see how much methane can be produced. And of course, we were also very curious about the kinetic rate constant so that we can see the results. In the results part, you can see that on the left, these are, of course, all gram VS or kilogram cubic meter. This is the raw herd, which was the witness material with various NS and F values. So the blue one is Navisarai and the other one is the Futura. So we checked and compared these two varieties of cannabis. If you look at the methane production per volatile material, it's very obvious. You can see that the chemical pretreatment creates accessible level of the biodegradable material. You can see the increase on the graphic. But of course, these might sound very optimistic, but if you can even achieve the half in really big tanks, it's a really important achievement, because even 10% increases in large industrial sites is a benefit. So within the matrix, we also try to show the alkali and thermal temperature for 20 minutes. This is the difference shown. On the left side, you have the raw herd. On the right one, the orange one, where the alkali and thermal is combined. On the right part, for the Futura variety, you can see that the difference is almost doubled. And this is really, really optimistic. And there is also another part of this study that I cannot show you right now, but maybe I can show you in later meetings. And this study basically simulated the large industrial sites. In the meanwhile, Professor Jale also helped us, and she also worked on whether these products can be used as biocoal. Maybe we will present them in a later study. This is the plots of the measured and predicted CH4 yield of F experiments. You can see that it is almost beyond 99%. So there is a really high level of harmony. And from the BMP classical graphics, on the y-axis, you see the gas potential. On the right side, you see the duration of fermentation. And in the pre-treatment, for instance, in the raw process, you can see that the period goes up to 20 days and more. But with pre-treatment, you can lower this down to 10 or 12 days. So it doesn't only increase the potential for biogas, but also helps you to get the facility smaller and switch to a more economical facility, which will help you increase the capacity and, of course, design benefits of the facility. And these parameters will help you set all those benchmarks. We also checked the structural changes. Professor Jale and her team did this part of the study. This is the pre-treated herd, and you can see the cellulosic changes in the structure. And we considered, of course, the results here. And it's very, very obvious that with the deterioration of this part, the molecules that those bacteria can reach is shown here. So as a conclusion, and I have used my time, I think very nice. And so I can say that in the study, the BMP of hemp herd of Ennis and F varieties and the effect of chemical pre-treatment were investigated. These obtained results were similar for alkali and caustic pre-treatment. We tried to use the thermal application, increased the BMP of herd of two varieties. In a biogas facility, you of course don't want sodium or potassium to be involved in the facility too much. That's why you have to make a balance there. But in our studies, of course, in our trials, we have seen that there was no negative impact. I would like to thank you so much for giving me the opportunity. And I would like to thank also the ministry for their contribution, the Black Sea region, and of course TÜBİTAK. Of course, you know, TÜBİTAK is one of the only and probably the only source of income for us. And hopefully we will present the results then. Thank you so much for bearing with me.
Thank you very much. Of course, I don't want to thank to myself, but still, you had concluded in time. I am having a look at the questions. Hüseyin Akkol, I think, among the provinces allowed cannabis growth, we have now Sivas, and in total, it's 20 provinces, which is very good because it means that this raw material is getting wider in terms of its scope, which is very nice. There is another question. I don't know the name. Maybe I have missed it because I was late, but what is the ratio of the methane in the biogas for two different types of cannabis? And which method do you suggest in isolating methane? I think you cannot see me because I'm not allowed to turn my camera on. Okay, at least you hear me. Let me answer. It's between 60 to 68% methane wealth or methane richness. And the other question was related to the real-time applications. If you allow me, I have a different presentation in 3 p.m., which is related to biomethane generation. There are at least 10 steps, beginning from scrubbing to membrane processors. And we have another system, a patented system. So about CO2 removal and its use in transport and natural gas line, it's not very easy. They are not very easy procedures. We have many physical-chemical steps to be taken. If you can listen to me, my presentation at 3 p.m., I will be sharing all this. Thank you very much. In the chat part, we have voting links. I don't know what they are. Please click in the links. I see a question. Maybe you can answer. About cellulose, when we look at the copies method is not very good. There are some modified methods. I will be providing him with the literature which we've used. Another question is asked, I will this whole in the afternoon session. This was the question. His first presentation will be mine. So we will not be allowing Nuri go away. May I take floor, please? The voting links are actually surveys. Could you please share it? And there will be scoring for the surveys. Please use the links. I think I didn't have a similar thing. Okay, I will be sharing for the next presentation. Okay, let's do it. Yeah, I have just seen for Nuri. Thank you very much for the information you've provided. Thank you. We are keeping up with the program. Our third speaker will be Muhammed Rashid Atelge, who will be speaking about evaluation of applying pretreatment with electroporation to enhance the quality of feedstock for biogas production as biofuel. I don't know Mr. Muhammad. I think during his presentation he will tell us. And floor is his. Yes, Mr. Atelge, Muhammed Rashid Atelge, are you there? I think he's not here. Sorry, now mic is on. Could you please introduce yourself too? Sure. My name is Muhammed Rashid Atelge. I am coming from Siirt University. I've recently completed my PhD. Of course, it's very exciting to make presentation before such experienced professors. I hope you will forgive my mistakes. Mohammed, we have among friends here, no problem. And we have listened to Nuri too, and he had organized a conference a few months ago. I hope I will be taking your recommendations related to going forward. Let me share my screen. Rashid, you can turn your camera on. I see coffee beans. Hello, everyone, again. We will be discussing pretreatment with electroporation to enhance the quality of feedstock for biogas production as biofuel. First, I will be sharing a background with you. Then about how to treat the coffee beans, how it is recycled, how it's good for AD processes, the advantages and results of this. As the human beings, we are producing a lot of wastes, including municipal waste, agricultural waste, and industrial waste. Most of them have high organic compounds, and we need a high level of oxygen. And there are methane and carbon dioxide within them. And in terms of global warming, CO2 is 20 or 25 times more harmful. Sorry, methane. And of course, there are some for example, in UK, for 1 ton of waste, you have to pay 85 euros. That's why it's opening an important door in order to produce waste products and energy. Another important topic is recycling of waste for bio waste. Why we selected coffee? Because coffee is the second largest traded commodity after petroleum, and it's the second consumed beverage after water. Of course, if we are throwing away the coffee grounds after it's being drunk, it is really harmful for the climate, and there are around 5 billion cups of coffee consumed on a daily basis. According to International Coffee Organization, between 2015 and 2019, more than 10 million tons of coffee products were consumed worldwide. And coffee industry generates around 6 million tons of waste per year. So 1 kilogram coffee produces, I am referring to filter coffee, we are having around 500 gram to 700 gram coffee ground. Then how to make use of it? It has a high carbon content, and it might be apt for biogas generation. In biogas generation, we have around 4 steps. The first one is hydrolysis, where the big constituents are divided into smaller pieces. The compounds are decomposed into small compounds. In the second phase, we have acidification. The small compounds are being turned into acetic acid, and the methanogenic phase is the phase where methanogen bacteria make up 70% from acetate. What's important here is each waste has a high biogas potential, but in real-time applications, we cannot have enough level of biogas generation. That's why we need a pretreatment. As Professor Nuri already stated, when we make a pretreatment, the methane productivity increases importantly. But in this pretreatment, we will have possible 3 scenarios. The green line shows a normal biogas plant. The curve is over time. The green line is without pretreatments. Mohammed, sorry. But rather than preliminary information, could we focus on the conclusions? Because you have already around only 9 minutes. Let me dwell upon this. Why Turkey is important in coffee is important in Turkey. Coffee consumption is increasing year by year in Turkey too. We have around 1.1 gram per capita. We don't grow coffee, so it causes import deficit, and it's very important to use it in economy because we are losing money in terms of this. What are we doing? We are collecting the coffee grounds from the coffee shops, and we are using an electroporation pretreatment. And we have done soluble chemical oxygen needs. So far, we could continue this study. Still, we don't have the final analysis, but we are working on the biogas generation. We are using high tension. We have a high tension system. We have a reactor here. It has positive and negative terminals, and we are implementing electricity. And we are implementing electricity current over the raw material. Once we have implemented this, in order to see the difference in between, we had carried out soluble chemical needs tests. We are using 2 solvents. One is soluble, the other one is destructive. We are mixing these solvents we are keeping them in 150 Celsius degree for 2 hours. And we are using wavelength, and we are analyzing the soluble oxygen needs. We had 2 samples. One is coffee waste, and second one is pretreated coffee waste. When we look at the soluble oxygen needs, the blank sample has around 650 milligram per liter soluble chemical need, but when it is pretreated with electroporation, we have 4 or 5 times more, 404,000. The speaker says 650 milligram per liter, but apparently it's 750, which means that our biogas generation will be much faster, because still we are working on the experiments, because so far we cannot say that it is contributing to the amount, but it is certain that it is contributing to the generation speed, the speed of generation. I don't have much data about this. That's why I want to conclude my presentations. If you have any questions or recommendations, I will be happy to hear them. Are there any questions? So far, I haven't seen a question. May I ask? I'm not a biogas person, but still, maybe my question will be bizarre. In electroflotation, what is the change in the structure? We haven't looked at the structure so far because we have started recently. I have completed my PhD around 4 months ago, and we have started the study 2 weeks ago. We will be possibly breaking limpin layer in the coffee, and biocellulose will be more available. We haven't proved it yet. We couldn't complete the studies. What about the literature? It says that it is eliminating hemicelluloses. So it's in the same direction. So is it just eliminating hemicelluloses with lignin? Lignin is being eliminated. Okay. It's interesting. And cellulose and hemicellulose is very important in structure. I'd like to learn the method you have used, because Deduman already shared the literature which we have used. We are using a modified method. It's quite applicable. The CAPE method is not good for any kind of biomass. Actually, we tried to use it, but it wasn't very efficient. But this method is quite good. It's working. And you can use the normal chemicals in a normal laboratory. Thank you very much, Professor, for this. And I have another question. The voting links only lives for 5 minutes. After 5 minutes, they are off. Because we cannot do voting. The fourth speaker of this session is Beril Gündoğan. Let me answer. According to 2018 data, we have a total $1.3 billion coffee import. He said export, but possibly it's import. Then I'd have another question. You are first drying it, right? Storage is after drying. Yes, we are first storing, then we are keeping it in 4 Celsius degree refrigerators. Possibly they include around 60% humidity. Yes. Also, it causes humid. It creates mold. I'm a thermochemical chemist. We had created this with this method, and it has a lot of lignin. Let me tell it to you. Yes, Professor. This is the biggest problem with us. Yes. Yes, first speak. Nuri Bey also wants to take floor. Yes, Professor Nuri. Rather than a question, just a very brief explanation. What does it do? You asked. Think of a sugar molecule. For example, compare it with the ground sugar, candy, and a syrup. But the bacteria is consuming syrup. You cannot give it to ground. The structures which we call sugar candies are not usable, so you have to solve it in order to render it usable. It's a promising method. Thank you very much. I congratulate. Thank you very much. I hope we will be in contact with you too. Any other question? I think no. $5 billion in 5 years. Is it the total export and the expenditures? I think this is related to coffee. It's 1.3 billion is for export. Okay, then thank you very much.
So we have to switch to the fourth speaker. Beril Gündoğan will take the floor, and she will be talking about the optimization of dilute acid pretreatments of Cynara carbonculus residues for biogas production.
Evet.
The floor is yours. I don't know if I have spelled the Latin correctly, but
herhalde bir problem yok.
all right, thank you so much.
Ben ekranımı paylaşıyorum.
Let me share my screen.
Tamam, tanıtacağım.
And please also introduce yourself.
Herkese merhaba tekrar.
Hello everyone.
Adım Beril Gündoğan. Ege Üniversitesi Biyokütle Enerji Sistemleri ve Teknolojileri Uygulama ve Araştırma Merkezi'nden katılıyorum. Sevgili hocam Profesör Doktor Günnur Koçar'ın doktora öğrencisiyim. Bu sempozyumunuza Cynara carbonculus kalıntılarının biyogaz üretiminde kullanılabilmesi amacıyla seyreltik asit uygulamaları, ön işlem uygulamalarıyla ilgili bugün size bir sunum gerçekleştireceğim. Ben öncelikle kısaca bitkimden bahsetmek istiyorum, yani materyalimden bahsetmek istiyorum. Cynara carbonculus aslında hepimizin bildiği yabani enginar olarak geçiyor. Asteraceae familyasının bir üyesi. Akdeniz bölgesine özgü çok yıllık bir bitki. Aynı zamanda kardon olarak da adlandırılıyor Türkçe olarak. 3 alt taksona sahip. Dünyada yaygın olarak üretimi gerçekleştiriliyor. Zaten son yıllarda da enerji bitkisi olarak hem farklı alanlarda hem de biyogaz çalışmalarında, biyogaz üretim proseslerinde yaygın olarak kullanılmaya başladı. Dünya çapında FAO'nun verilerine göre yaklaşık olarak 1.6 milyon ton kadar üretim gerçekleştiriliyor. Bunun çoğunluğu genelde Güney Avrupa ülkeleri, özellikle İtalya, Fransa, İspanya gibi ülkelerde. Türkiye'nin üretimine baktığımız zaman da dünyadaki üretimin yaklaşık %2,5 kadarını oluşturuyor. Türkiye'de de yine birçok bölgemizde üretimi gerçekleştiriliyor ama yaygın olarak Marmara bölgesinin kıyı kesiminde, Ege bölgesinde ve Akdeniz bölgesinde yaygın olarak üretiliyor. Özellikle de Ege bölgesi zaten Türkiye'de en yaygın üretilen bölgelerden bir tanesi. Çok farklı kullanım alanları var Cynara carbonculus'un. Çoklu kullanımlarının yanı sıra endüstriyel uygulamalarda da yeri var. Çoklu kullanımları burada özetlediğim gibi zaten yiyecek kaynağı olarak kullanılıyor. Bunun dışında geleneksel olarak peynir üretiminde enzim kaynağı olarak kullanılmakta. Birçok fenolik bileşenlere sahip yine farmakolojik çalışmalarda kullanılmak üzere. Aynı zamanda yine son yıllarda karşılaştığım çalışmalardan bir tanesi de fitoremedasyon çalışmaları. Endüstriyel uygulamalarına baktığımız zaman piroliz ve gazlaştırma çalışmaları, sahip olduğu yavru tohumlar sayesinde biyodizel üretiminde sıklıkla kullanılmakta. Uzun yıllardır yine kağıt ve kağıt hamuru üretiminde kullanılıyor ve son yıllarda da biyogaz üretiminde odak noktası olmuş durumda. Ben de bu çalışmada zaten onun üzerinde duracağım. Kısaca bitkimden bu şekilde bahsetmek istedim. Asit ön işlemleri, yani termokimyasal ön işlemlerden bahsedeceğimi söylemiştim. Termokimyasal ön işlemleri uygulamamın sebebi hepimizin bildiği üzere aslında lignosellozik bir materyal. Cynara carbonculus tarımsal artık diye de nitelendirebiliriz. Lignosellozik biyokütle ya da lignosellozik artık diye bahsettiğimiz zaman bu yapının selüloz,
And
hemiselüloz ve lignin bileşenlerinden bahsetmek durumundayız. Bu lignoselülozik yapının hücre duvarında bulunan bileşenler. Bu yapı oldukça kompakt bir yapı. Hem enzimatik ataklara hem de mikroorganizmaların aslında hidrolize edebilmesinde, parçalayabilmesinde oldukça zorlandıkları yapı. Biz de bu tarz çalışmalarda yani biyogaz üretiminde ya da daha farklı biyoyakıt çalışmalarında, biyoyakıt üretimi çalışmalarında kullanabilmemiz için aslında bu yapıyı biraz olsun yumuşatabilmemiz gerekiyor. Literatürde zaten ön işlemlere bakıldığında lignoselülozik biyokütlenin ön işlemlerin incelendiğinde mekanik yani fiziksel ön işlem, kimyasal ön işlem ve biyolojik ön işlemlere rastlamaktayız. Fiziksel ön işlemler kısaca lignoselülozik yapının yani materyalin biraz daha boyutlarının küçültülebilmesine yönelik herhangi bir yapıda kimyasal bir değişime sebep olmuyor. Bununla birlikte biyolojik ön işlemler daha çok ticari enzimlerin de kullanıldığı, çeşitli mikroorganizmaların uygulandığı ön işlem çalışmaları. Kimyasal da birazdan bahsedeceğim üzere asit, alkali ve daha başka kimyasallar olmak üzere materyalin kimyasal yapısında değişimlere sebep olan ön işlem teknikleri. Ben çalışmamda termokimyasal ön işlem olarak yani aslında seyreltik asit uygulamaları gerçekleştirdim. Bu çalışmam benim biraz daha optimizasyona yönelikti. Çalışmada 4 asit kullandım, 4 tane inorganik asit kullandım. Burada gördüğünüz sülfürik, hidroklorik ve nitrik asit zaten lignoselülozik biyokütlenin kimyasal ön işlemlerinde yaygın olarak kullanılan inorganik asitler. Ben bunlara ilave olarak borik asit denemesi de gerçekleştirdim. Aslında sülfürik asit, hidroklorik ve nitrik asit oldukça güçlü asitler, yapıda oldukça yapının hidrolize edilmesinde oldukça etkili olan asitler. Fakat borik asit diğer 3 asite göre biraz daha soft kalan bir asit ama ben yapıdaki değişimleri yani biraz aradaki farkı görebilmek amacıyla bunu da denedim. Şimdi kısaca seyreltik asit ön işlem uygulamalarının lignoselülozik biyokütle üzerinde ne gibi etkisi oluyor? Biyogaz üretiminde biz bunu neden kullanıyoruz? Ben kısaca bundan bahsedeceğim. Söylediğim gibi lignoselülozik biyokütle selüloz, hemiselüloz ve lignin bileşenlerine sahip. Bu yapı oldukça kompakt bir yapı.
Beryl, excuse me, but you have 7 minutes. Maybe you can start talk about the results.
Tamam. Buradaki amacımız bizim aslında kısaca mikroorganizmaların kullanabileceği 5 karbonlu ve 6 karbonlu şekerleri elde edebilmek. Yani bu kompakt yapıyı birbirinden ayırarak özellikle de hemiselüloz yapısının bu görmüş olduğumuz 5 ve 6 karbonlu şekerlere ayrışmasını, hidrolize olabilmesini sağlamak. Sinara karbonkulus artıklarını ben özellikle 1 ve 3 milimetre arasında olacak şekilde ayrıştırdım ön işlemlerde kullanabilmek üzere. Design Expert yazılımı kullanılarak Boxbank'ın deneysel tasarımı yaptık. Buradan istatistiksel modelleme yaparak termokimyasal ön işlemlerin optimizasyonunu gerçekleştirdik. Bu tabloda parametrelerimi ve bu parametrelerin aralıklarını görüyorsunuz. 3 değişkenim vardı. Bu sıcaklık, asit konsantrasyonu ve bekletme süresi yani reaksiyon süresi. sıcaklıklar ve asit konsantrasyonu, bekletme süresi aralıkları tabloda gördüğünüz şekilde. Şeker elde edimine etkisini görmek amacıyla ben bu aralıkları belirledim. Yapılan ön işlemler sonucunda HPLC sıvı kromatografi cihazında monomerik şeker içeriklerine baktık. Sellobiyoz, glikoz, kisiloz ve arabinoz. Söylediğim gibi bu şekerler biyogaz üretiminde kullanılmak üzere, yani katı lignoselülozik materyalimin katı ve sıvı fazın, hem katı hem sıvı fazını mikroorganizmaların kullanabileceği hale getirmektir. Hemen sonuçlarıma geliyorum. Bu tabloda istatistiksel analizler sonucunda 4 asidinde R kare, modele ve Profef değerleri var. Bu Design Expert programından elde ettiğim R kare değerleri burada 100 örnekte 99, 98, 97 ve 95 örneği açıkladığını gösteriyor. HPLC sonuçlarıma baktığımda sol taraftaki halka içerisinde gördüğünüz benim optimum koşullarımda. Bu optimum koşullar neye göre belirlendi? Total şeker miktarına göre en yüksek şeker elde ettiğim sıvı fazdaki en yüksek şeker miktarlarını vermekte bu tabloda. Bu çalışmaların yanı sıra tabii ki de validasyon çalışmalarını gerçekleştirdim. Programın bana vermiş olduğu ön işlem koşulları, bununla birlikte beklenen total şeker miktarı, en sondaki sağ taraftaki de benim elde etmiş olduğum validasyon çalışmalarına baktığımızda da çalışmaların oldukça uyumlu olduğunu görebiliyoruz. Sonuç olarak ben tüm bu denemelerim sonucunda 4 asit içerisinde nitrik asit uygulamasında özellikle en yüksek monomerik şeker eldesi gerçekleştiğini gördük. Zaten literatürde inceleyecek olduğumuzda özellikle seeratik asit uygulamalarında nitrik asit son zamanlarda yaygın olarak kullanılmaya başlamakta. Bunun sebebi ise nitrik asitin özellikle hemiselülozin hidrolizinde ve selülozun bir kısmi hidrolizinde oldukça etkili olması ve böylelikle de monomerik şekerlerin daha yüksek eldesini sağlamış oldu. Söylediğim gibi bu sinara karbonkulus artıklarını ön işlem, kimyasal ön işlemlerden geçirdiğimizde ve biyogaz üretiminde kullanabilmek amacıyla, yani anaerobik fermentasyonda kullanabilmek amacıyla mikroorganizmalara aslında biz substrat sağlamış olduk. Ben burada bu çalışmada biraz daha şeker üstünde durdum. Tabii bunun katı fazın analizleri de var fiber çalışmalarıyla birlikte. Onlarda da HPLC sonuçlarını destekledim ama bu çalışmamda vermemiştim. Bununla birlikte en düşük sonuçlar borik asitte elde edildi. Daha az bir hidroliz gerçekleşti. Bu da beklediğim bir sonuçtu zaten. Söylediğim gibi bu diğer 3 asit, çünkü borik asite göre biraz daha kuvvetli bir asit. Çalışmalarımın özetine baktığımızda sinara karbonkulus atıklarının özellikle hayvansal atıklarla birlikte kofermentasyonda kullanılabilmesi için anaerobik fermentasyon aracılığıyla biyogaz üretiminde ben seeratik asit uygulamaları gerçekleştirdim ve en iyi sonuçları da nitrik asitte görmüş olduk. Ben çok teşekkür ediyorum. Sunumumu olabildiğince hızlı yapmaya çalıştım.
To keep it brief. Thank you very much. And you finished 1 minute before. Okay, thank you. Thank you very much.
Ben teşekkür ederim hocam. Şu an ekranı göremiyorum ama.
I cannot see the screen right now, but
Tamam hocam, döndüm. Ben teşekkür ederim beni dinlediğiniz için.
Thank you so much for your attention. So now let's switch to the questions. Ramazan, I think, asks a question. Whether you had the analysis of uncertainty.
Derken validasyon çalışmaları.
What do you mean by uncertainty? Do you mean the validation studies? Could you raise your hand, Ramazan, so that you can discuss your question? Ramazan, can you hear us? If you hear, please raise your hand. Can you hear me? Yes. Well, when the results are announced, the quantity
Evet.
of sugar is given. Probably it wouldn't be so much in reality. So what is the uncertainty? So you made the measurement, but of course there are also error margin for the device. I mean, have you had
Ben
this
hocam şu
experimental
şekilde bir
uncertainty
analiz yaptım.
study?
Validasyon çalışması
Well,
gerçekleştirdim.
I
Buradaki
did validation
cihazın
study
acaba
to
doğru sonuçlar
see
mı
whether
veriyorum,
the
her
device
defasında aynı
gives
sonuçları mı
accurate results, whether we receive
edemeyeceğimi
the
görebilmek
same
için
results every
validasyon
time.
çalışmaları
So
gerçekleştirdim. Bu
yes, I
çalışmaları
did
da
validation
bu istatistiksel
studies,
analiz
and
programında
of course we used the statistical analysis
ismini Design Expert
software. It was
programında
Design Expert, I
programın
think, yeah.
bana rastgele verdiği
And the
parametrelerle
software gives us
parametreleri
random
doğrultusunda
parameters,
ön işlem
and
çalışmalarını tekrar yapıp
so I
tekrar
did the
verdiğimde
pre-treatment
programın
actions to
istediği
check
sonuçlarla kendi
whether the
kıyaslarımı,
software
kendi
gives
sonuçlarımı kıyasladım ve
me the same results.
doğruladı. Zaten onu da
And
tablo
it's
olarak
basically
vermiştim.
validated, and I included that on the table. Yes, but that is the deviation. What I'm trying to say is something else. Let's say you measure 42 milligram, but basically it would never be 42 milligrams. There will be always a margin of error. That's why I'm asking whether you had this experimental uncertainty. So from the measurements you had on the HPLC, both from the device or both from the author, there will probably going to be certain errors.
Belirsizlik sonuçlarım yok şu an için.
Well, no, I don't have the uncertainty results yet. And one more question. Now that you have the sugar output, are there other outputs that will damage the environment? Do you only have sugar? Nothing else?
Dinliyorum. Doğaya zararlı olacak şekilde değil. Baktığınızda zaten asitlerle çalışıyoruz. Doğaya zararlı olacak olmak üzere değil de şu şekilde tabii ki şekerlerin yanında bununla birlikte farklı inhibitör bileşikler çıkıyor. Bunlar furfurallar olmak üzere özellikle anaerobik fermentasyonda mikroorganizmaları inhibe edebilecek farklı bileşikler de tabii ki ortaya çıkıyor. Onların da ayrı farklı şekillerde analizleri yapılıyor. Çünkü kimyasallarla çalışıyorsunuz ve orada bir aslında yapıyı bozuyorsunuz. Dolayısıyla sadece bizim istediğimiz o mikroorganizmalar için gerekli olan substratlar ya da şekerler ortaya çıkmıyor.
So even if you, of course, it will be better to have a BMP test too on this part, because BMP test gives you the biogas potential. Yeah, my studies are ongoing on an experimental basis. And if you are good at the Latin, let's talk about the residues of artichoke. So rather than talking about the Latin names, let's call it artichoke residues, all right? Because as Aegean people, we use artichoke very much. So let's name it artichoke rather than its Latin name, which is extremely difficult for us to memorize.
Teşekkür ediyorum.
Thank you very much once again. Thank you. Thank you for this nice presentation. Thank you so much. And the fifth presentation will be delivered by Yonca Kılıç, and she will be talking about the biodegradability of low biodegradable agricultural waste in bioreactors, sunflower stalk example.
Gonca, could you introduce yourself? I am coming from the environmental environment. department, and I am working on biomass processing and biodegradability of low biodegradable agricultural waste in bioreactor, and I will be focusing on sunflower stalk. Could you allow Yonca to share her screen? Yes, Jalim. And your name, please? I am Neil. Yes, sorry. Could you share it? It's biodegradability of low biodegradable agricultural waste in bioreactors. Sunflower stalk example. Solid wastes in our country are considered among the important environmental problems due to their excess amount and high pollution potential. When the characterization of solid waste was investigated in Turkey, showed that approximately 55% of the organic waste this is organic waste. When we look at the other waste, plastic it's 5.68, metals 1.37%. In table 1, you see the solid waste characterization in Izmir. You see that in 2018, between 2013 and 2018, when the characterization is looked at, we see that kitchen waste have an organic waste content around 76%. When we classify the solid waste, they can be named according to places where they are created: domestic solid waste, medical solid waste, hazardous solid waste, industrial solid waste, agricultural and garden waste, construction waste, and debris. In domestic solid waste, you see the amounts. When you look at the shape, you see that kitchen waste is around 2.3 million ton per day, which constitutes 41% of all wastes. Rather than the general information, could you focus on your study, please? Since I have industrial solid waste, urban solid waste, I wanted to give a brief background about this. Now I'm about to proceed with my part. Agricultural and garden waste, plant residues in parks and gardens, organic plant waste from agricultural activities, and waste such as brushwood waste in similar places. Agricultural wastes are divided into 3 groups. These are waste generated during or after animal production, waste generated during or after vegetative production, and waste generated during or after the production of agricultural products. Interpreters note, the speaker is reading through our presentation, that's why we are reading through it. Waste generated during or after agricultural activities. It is the waste generated during drying, grinding, and sorting before starting to cultivate the soil for the production of agricultural products. During and after the cultivation of the soil, from the moment the agricultural product is planted in the soil, during the growth, development, and harvest period, and afterwards, stalk, straw, seeds, roots, leaves, branches, etc., and other wastes occur. These wastes are among the wastes generated by the processing of agricultural products. According to Turkstat data, the products grown in Turkey and the amounts, we see that wheat, barley, corn, and sunflower. When we look at the table, They are generally called grains, except sunflower stalk, the wheat, barley, corn, and others are used in agriculture. Nearly 90% of the stalks are in waste position, and it's very important to create added value from them. When we look at the table, we see the sunflower production in Turkey. Tekirdağ is the leading city with 19%. You see various biomass sources. In Turkey, our energy need is growing day by day. It's extremely important to evaluate waste as an energy source. Biomass resources include the vegetable waste and the leaf waste, and you see the methane vegetable scraps around 330 to 360 biogas efficiency, and methane ratio is variable. Wastewater sludges has a biogas efficiency between 310 to 800, and this methane ratio is between 65 to 80%. Vegetable scraps are variable according to these data, but it generally varies between 50 to 60%. To define my bioreactor, the bioreactor landfills are closed-end control systems that ensure the rapid degradation of the organic path of the waste and the formation of stable waste in a short time. Bioreactor landfills aim to minimize the environmental impacts that may arise from storage, as well as to operate the stored waste in a way that it becomes stable in a minimum time. The main process applied in bioreactor storage areas is to transfer the leachate generated during waste decomposition back into the storage area. The recirculation of the leachate not only provides an environment where biodegradable waste can be decomposed faster, but also provides partial treatment of the leachate. I used anaerobic and aerobic bioreactors. Speaking of anaerobic bioreactors, they accelerate the degradation of waste by optimizing conditions for anaerobic bacteria. This is done by providing a high moisture content for anaerobic bacteria to thrive, which is around 35 to 45% of the humidity. They are an anaerobe environment. Methane bacteria can reproduce, and in this way we can generate electricity. Yonca, you have only 9 minutes for the experimental part and conclusions. Okay, let me summarize this too. Why I used aerobic anaerobic bioreactors? Because aerobic reactors have a fast decomposition, and anaerobic has an advantage in methane bacteria and to stabilize the remaining part. That's why we have used these bioreactors. The scope of my study: the characterization of leachate samples from solid waste simulated anaerobic and aerobic anaerobic storage bioreactors was carried out. The leachate samples are COD, pH, VFA, NH4, -N, BOD3, water content, organic matter, TKN, total gas and methane gas production, municipal solid waste taken from Pamukkale University Central Dining Hall, and stabilization of sunflower pruning waste obtained from the sunflower field was monitored in simulated anaerobic and aerobic anaerobic reactors. They had been monitored. The materials and methods: these are lab-scale simulated bioreactors. You can see it in figure 6. It's a reactor produced from stainless steel. It has a 2 liter of reactor volume. When we look at the flow chart, we have a sampling valve, and we have a valve for having air, and circulation is created through the sampling valves, and the gas content is measured from the hose coming from the valve, and we have a rainwater addition valve in order to add water if necessary. Loading solid waste into anaerobic bioreactors. I have pre-treated them physically. I didn't pre-treat them chemically or in any other way. and I decrease the size. In one of the reactor, we have 20 to 50% urban solid waste and sunflower stalk, and the other one is 50% municipal solid waste and 50% sunflower stalk. I used anaerobic treatment sludge as feeding material. In order to give humidity content, we have used chlorine-blown fountain water. Anaerobic treatments or processing conditions was as in this way: loading solid waste into anaerobic bioreactors. Again, the same conditions, 20% to 80%, and but this was hard to decompose. Then I used 100% sunflower with the same. In the aerobic one, I used 20 to 80%, but in the anaerobic one, I used only 100% sunflower. Addition of anaerobic treatment sludge as feeding material and chlorine-blown fountain water, but I added an air pump to reactor. The analytic procedures, I'm skipping this. COD, pH, gas measurements, ammonium, nitrogen, TKN, BOD, water content, organic matter. These are made according to standard methods. Conclusions. The COD concentration in reactors, in different reactors, is having a variable content. When we look at this figure 1 and figure 2, we have 22,026 milligram per liter in reactor A, the COD concentration, and it is the 195 milligram per liter for the reactor B. When we look at the end of the operation period of 90 days, the COD concentration in reactor A was 651 and 1,326 milligram per liter in the reactor B. When the COD removal efficiency are calculated, the COD removal efficiency in reactor A is 97% and 94% in the reactor B. At the end of the operation process, we observed an increase in 94% and 97%. The reason for this is that anaerobic process is faster than the aerobic process. The acidification phase is faster and it can permeate into the water in the shorter time. pH change in leachate samples taken from solid waste reactors. When the pH values under anaerobic operating conditions are examined, we see that there is a difference, because after the hydrolysis phase, there is a pH decrease because of acidification process. In order that the methane activation might continue, we are adding alkali, and I added this with sodium bicarbonate. This continued for a while. After having the optimum pH conditions, without adding anything else, we had concluded the operation of the reactor. There wasn't a decrease in pH values. That's in the anaerobic one. That's why I didn't add alkali. You can see this on the figures. When we look at VFA concentrations in leachate samples, we didn't look at it in the aerobic systems because it's volatile. But when we look at the anaerobic one, you see the differences on the table. And we continue to observe a decrease in the upcoming days. Cumulative total gas amount in solid waste reactors. When we're looking at the figure 10 and figure 11, in anaerobic bioreactors, the cumulative total gas amounts was calculated as 12,420 liter in reactor A and 1,875 liter in reactor B. In anaerobic conditions, it was 29 and 52 liters. Anaerobic is more optimum. Of course, this is not 12,000, but only 12. the cumulative methane amount and percentage in solid waste reactors. Looking at figures 12 and 13, the cumulative amount of methane in anaerobic bioreactors was calculated as 6.23 liters and in reactor A and 9.405 liters in reactor B. Approximately 53% of the total gas generated in the reactors is methane gas produced in anaerobic conditions. When we look at the aerobic bioreactors, cumulative methane amounts had been determined 11 and 20 liter, and 50% of total gas generated is methane. Biochemical oxygen demand concentration in leachate samples taken from solid waste reactors. You have only 2 minutes. It was a very intensive study, and if you didn't go into the details of the introduction, if you know, this is all I could make shorter. The BOD-COD ratio is an important parameter. Lignin and cellulose content was high. In the beginning, it was between 0.2 and 0.18, which shows that they have low biodegradability. When we look anaerobic ones, the BOD-COD ratio is higher. At the end of the 90 days of operation period, it was set as 0.5 and 0.4, which shows that aerobic conditions lead to a higher degradability. When we look at the leachate, the ammonium, could we proceed with the conclusions, please? Your time is over. We cannot eliminate ammonium nitrogen. In the other one is turned into nitrite and nitrate. This part is important. The water content is 71% and the organic content is 82% in anaerobic one. And it's 50% for the anaerobic and 60% for aerobic. To wrap up, the studies show us this. Due to high lignin and cellulose content of agricultural waste, the degradation process takes place in long stages with anaerobic treatment methods. Therefore, it has been determined that agricultural waste are broken down with pre-aerobic treatment in order to accelerate the breakdown process and then operated anaerobic for methane production, contributing to the degradation process of waste. According to the analysis results, the COD concentration in the leachate samples taken from the reactors on the 30th day under anaerobic operating conditions is 21,000 and 12,000, respectively, in reactor A and reactor B. In reactors that started to be operated aerobic for 30 days and subsequently operated anaerobic, the COD concentration in the leachate samples taken from the reactors on the 30th day is 3,000 milligram for reactor A and 2,300 milligram for reactor B. According to the results of the analysis, shredding of agricultural waste in reactors operated by giving intermittent air was determined as an appropriate method. Thank you, Yonca. Are there any questions? Mehmet asks for floor. Mehmet, yes, you can take floor. I think Mehmet cannot. I'll let floor to him, but I cannot hear him. Okay, let me have a question. As a biogas aficionado, okay, in order to increase degradation in aerobic reactors, first you do an aerobic operation. Yes, I give air. You don't produce methane here. Yeah, we produce methane, but it's not as much as the anaerobic. And then I give an anaerobic in 60 days. pH is between 7.72, 8.42 pH, but in the anaerobic part, pH part is too high. That's why the bacteria waits for a while, but in this way I can control it. And when do it in the aerobic manner, in the remaining part we don't have a lot of decrease in pH, but our efficiency is higher. What if you have done a pre-treatment and then an anaerobic? Before doing this study, I have looked at the pre-treatment, but there's a problem. Heat and chemical pretreatments are treated differently in the literature, but sometimes they can produce side products as methyl 5, which are inhibited methane activity. So it will be a negative effect for me. That's why I didn't use it. On one hand, I had looked at how I can decompose it physically. But as an environmental engineer, it's important for me to consume less. That's why I selected mesophilic. Otherwise, if I have done it thermophilic in 55 Celsius degree, methane production is higher, but it's a cost too. If I will use more electricity than I've generated, it doesn't make any sense. I have looked at the minimum levels. Serdar wants to have floor. Serdar Bey, can you take the floor? And then Serdar Bey, turn your microphone on, please. Could you turn your microphone on? No message either. Sorry, there was a problem. In the anaerobic part, what was the difference? Exact difference in terms of methane production? What was the change when you give air? I did it for 30 days, and in the remaining 60 days, it was anaerobic. When I compare it with anaerobic, of course, methane is produced less, and the reason for this, that we don't have an oxygen bound here. Since I provide oxygen, in anaerobic, it was 50%. In aerobic, it differs between anaerobic, it differs from 20 to 30%. Even if we don't have, even if we have a low level of oxygen in the environment, the groups can be impacted from them. And we have a lot of decrease in methane generation. I studied this too, so that's why I wanted to learn the difference. 20% to 20% difference, and then the efficiency went up to 60%. Osman Nuriada. Yes, he has the floor. Can you hear me? Yes. Professor Dr. Osman Nuriada. I am Yoncas consultant, PhD advisor. About aeration of the reactor. Is it aerobic too? We are doing an intermittent ventilation. Oxygen comes in. Then fast decomposition start, and then we stop air inlet. Then we make a partial ventilation. Then anaerobic process starts. Especially for the organic compound, which is hard to decompose, we use this phase in order to cut through or bypass the organic phase. Thank you, Professor. I have forgotten this detail because of excitement. Any other questions? I think no. The last presentation.
All right, the last speaker in this presentation is Işık Semerci. I'm checking the PDF program, so thank you very much for joining us. The title is Biomass Processing and Valorization with Photic Ionic Liquids. The floor is yours. Thank you very much. I'm from Ankara University, Department of Energy Engineering. And if you allow me, I would like to present in English. Well, just please finish in 15 minutes.
Işık Hanım, biraz çalışmanıza gelseniz 6 dakikanız kaldı. Biz teşekkür ederiz. Çok ilginç bir çalışmaydı.
Thank you so much. It was quite interesting.
Yeah. Who is speaking?
Hocam İngilizce kanalına çıkmanız gerekiyor. Tercümeyi duyuyorsunuz çünkü.
Ha, pardon.
All right. Well, it was a really interesting study, and I believe there are going to be questions from the audience. Is there any question? All right. So let me ask you a question. You have pointed out that the ionic liquids are recyclable. However, within that ionic liquid, isn't there also disturbed linear components? Well, basically, we can talk about hemicellulose derivatives. Linear also probably will have, because 60% of it is removed. Yes, approximately half of it is removed, and we try to get as much as we can. So you basically use a solvent, you remove it, probably it's a phenolic component, am I right? So you take the phenolic component. So then, I mean, when you calculate the cost, do you also calculate the reactor charge, the quantity of the load or charge? Do you also take that into consideration? And what is the quantity of the ionic liquid? Well, I have not, worked on the anaerobic part, so I don't have much knowledge, to be honest, on that part, but during the pre-treatment, the level can go up to 30–40%. So how much do you use compared to the biomass, let's say? How much liquid you use? Well, compared to the biomass, I think it's like the double of the quantity of the biomass. Let's say 1 gram biomass, 2 gram ionic liquid is used. So it sounds like a little bit expensive, but maybe biogas experts can also contribute on that part. I don't know. They can also ask the questions. Well, we have never researched the biogas part, but I just also want to point out that we take the cellulose and lignin. However, we don't have any other treatment. We never research for alcohol or biogas production, so we don't use them for those purposes. For this reason, if there are experts or researchers that would like to join or take us to their studies, we will really appreciate. I think it's a nice example for the valorization of lignin, because you create a chemical, let's say, which is really valuable, but not too much volume, then it will be a really good idea to use it. Yes, acid and alkali will be better for that purpose. But for lignin valorization, yes, this will be a nice approach. And I also would like to ask you, let's say, the remaining cellulose or hemicellulose or lignin ratios in the mass. How do you identify that volume? We use the NaL approach. Yeah. All right. Thank you very much. Is there any other question? I see no hand raised. I think there is no question. Okay. Thank you so much, Dan, for this interesting talk and study. Thank you very much. So we would like to thank all the panelists and the audience. So we hereby adjourn this meeting now. Now we have, I think, 10 minutes break, and the next session will start. We have a 10 minutes coffee break. We will reconvene at 3:35. We started a little bit late, so all right. So see you in 10 minutes. Thank you. All right. All right. Thank you.
Welcome to the second part. We will be listening to Dr. Bülent Sönmez from TAGEM. We have 45 people here, as far as I see. And we have 7 presentations in this part of the afternoon. The first presentation will be by Mr. Nuri Azbar. I don't know if he's here. I'm here. Nuri Azbar will be speaking on enhanced biogas production and recent innovations in biogas technologies. Yes, please, floor is yours. You have 15 minutes. And you will have a warning in the last 5 minutes, and you already have experience because you had done your presentation. I have shared my presentation. Can you see it? Yes. Let me make an effective use of my time. Yes, biogas technologies, it's based on farm waste, have this flow storage process, and each point of the process is full of improvements potential, beginning from digesters, gas purification, and other places. We have this technology is being known since last 100 years, but day by day we are having new improvements. The biogas reactor configurations based on whether it is a farm type or it's based on aerobic and anaerobic process. So there are improvements for this too. I like this slide a lot. In Turkey, we have a high potential for the animal waste in terms of environmental friendly waste management. The biogas plants are providing a great opportunity, and it has an added value in terms of thermal and electricity generation. We know it's a complicated process. It's just like conducting a symphony orchestra. There are many biochemical reactions all following one another. And there are tons of things to be done. The electron channels, hydrogen-related improvements, we know that it is a triggering reaction after a while, especially in propionic acid production. We know that there are biochemical problems. I will not go into details because they are very issues, very deep issues. But looking from conventional point of view, we have a wet part using the wet sludge with a 5 to 15% water content. This process is mesophilic and it's a single stage. But recently we have drier, actually it's not dry, but humid, thermophilic, over 25 Celsius degree and over. Even there are hyperthermophilics, and these are more multiple stage systems. They are commercialized, and some of the plants in Turkey are from this background. Looking from commercially, especially we have to look at horizontality and verticality. There are different configurations. I am speaking fast because I want to make use of my time. Lots of interpreters, we will be doing our best to interpret it, to translate it. I'm sure that he says translators are angry with me, but I have to speak fast. 15 kilowatt for 1,000 cubic meter. We have great improvements. This had been decreased to 5 kilowatt. Mixing is very important, even if they are seen as full mixed reactors. But in order to have piston regimes, we need some hydrodynamic modelings in order to improve this blending part. Even we have colleagues who are doing their PhD thesis on blending. Solid biomass charging, it should, in order to ensure the circulation of the sludge, we have some mechanical equipment. It's not just like blending a washing machine. There are some designs which are looking from this primitive perspective, but actually we need nuances in design. I'd like to focus on dry fermentation. Even 90% of all biogas plants are composed of wet fermenters, but in recent 10 years, we have an increase in dry fermentation. Because in wet digesters, as you can estimate, if you are getting 800 ton material, you are getting out 800 tons of wet material, and there is a problem with their final disposition. But in dry fermentation, you are taking material in the cake form. In a garage type reactor, you can spray your nozzles and nearly dry material can be taken out of the system. Of course, it's not like a bone. It's not bone as dry as a bone, but still, it's like a cake. But in any case, you don't have to deal with the liquid part of this. These are the garage part types. There are even continuous one. This is a photo which I've taken. A plant which is working. You can load your agricultural, animal, brushwood, and other waste with working machines. And even if you have tin or other things, it doesn't have an effect on the system. If you will not use that as a fertilizer, it doesn't make any problem. And with an aerobic composting, you can bring it back to the field. Also, we have compogas, horizontal ones, and we had vertical ones. These are continuous heating systems. I don't want to make advertisements, but these are reactor configurations known globally. I don't want to go into their efficiencies, but their efficiency is close to wet digesters. They are a notch lower than them, but still there are so many advantages that it can be compensated. And you see that gas production per ton is not low at all. Pretreatment had been discussed a lot. Let me repeat them. Chemical, mechanical, thermal, and biological pretreatments. Especially the chemical pretreatments had been discussed. Alkaline and acid solvent usage had been discussed today. Ozone is a part of chemical pretreatment, but some of them are still in the level of academic research. They haven't been on the field because of economic reasons, but they are successful. They were successful in laboratories. The thermophilic ones are becoming more and more widespread in the fields in 55 Celsius degree. You know, while the temperature goes up, all biochemical and physical reactions accelerate by temperature. You see different physical-chemical processes, ozonification, solidification, ozonation, and phantom processes. This is implemented for treatment plant sludge, and you see there is an important increase in efficiency of gas, especially sonization had been commercialized. You see, it's just as big as an electricity panel. It's a 5 kilowatt plant. It can go to 20 kilowatt, but this is just next to a 3 megawatt. So a very small 15 kilowatt can increase your gas generation by 20%. And it begin to pay back this additional plant. There are some pretreatments related to decreasing particle size. In many examples, even decreasing the particle size up to 30 can have an effect up to 30%. You can see it, the maize, uncut maize, defiltrated grass, uncut, horse manure, uncut. And when you look our manure, maize uncut is decomposed easily, so you don't have to deal with the particle size. It doesn't give any significant results, but it's already easy to decompose it. Thermal conditioning is just like cooking a soup. The cellulosic materials, which are hard to fragmented, can be easily turned into sludge. We can see figures around 52%. These can differ from 10 to 20%, and there is an important economical payback. A very important improvement is micronutrients monitoring. If you are dealing with animal manure, there is no problem at all. In animal manure, their micronutrients are very rich. But if you use other energy sources like sugar bits uncut, grass uncut, grain uncut, many of them are not enough. If you are using monosulfate only for energy, you have to have a micronutrient deficiency screening in your plant. In recent times in Turkey, the organomineral fertilizer production is going hand in hand with the biogas generation, and it's very important in terms of giving advantage in economical and environmental improvements. In digester part, we have membrane systems where we can gain back or regain it. Even with the reverse osmosis, you can use this water in system or in irrigation. Of course, these are expensive systems, but when we look at the cost-benefit analysis, cost-performance analysis, sometimes we can have significant results. I have around 5 minutes. This part is important. This is a system which we have patented in Germany. Biogas system includes around 50 to 60% methane and 40 to 50% CO2. And this CO2 is idle. It's not being used. It just enters and goes out. You cannot burn it. And you cannot run a generator. We take this carbon dioxide and just next to this big plant, we are putting a very small equipment. There is a very complex chemical reaction here, but this is the simplified formula. We are infusing hydrogen from outside because the cost of it is based on hydrogen, so you have to be able to get hydrogen in an affordable price. You know, hydrogen electrolysis is possible, and the price is decreasing day by day. With this simple reaction, of course, you need an energy balance in order to get hydrogen, to produce hydrogen, and you can use biomethane for transport, or you can burn another gas from the CHP generator. In the CHP generator, I don't want to go into details of this, but you can enrich methane up to 85–90%, and per cubic meter reactor, you can go to 19 cubic meter. This is 1.5 to 3 cubic meter in conventional system. I'm sure my technical colleagues working on biogas would approve me. You can increase biogas production dramatically. And what's nice here, the methane values, the methane duration decreases from days to 10 or 15 hours. In last 5 minutes, I'd like to dwell upon the purification on biomethane production. In 2013, we had used it in the purification of biogas coming from the plants. We suggested that this could be used in mass transportation and also individual vehicles, and there are opportunities to compensate it in biomethane in automobiles, in buses. I have already showed it. For example, a garbage truck working with its own garbage. It's very nice and check publicity for us to. In a few minutes, let me wrap up. You can do it with wet scrubbing. There are many alternative solvents. Even lime can be used, one of the cheapest ones. In commercial ones, in polyglycol, you can capture CO2 and you can use it with enriched methane. Adsorption and desorption can be used with the pressure swing by implementing positive and negative pressure. You can purify methane in this way. In membrane press separation, you can pass it through the membrane, and by allowing the others to go through, you can have biomethane up to 85% to 90%. Also, if you are to send it to a natural gas system, you need to eliminate H2S. The existing plants already does this. Active carbon or ferrogranules are important with this regard. Also, you can use iron chloride, ferrum chloride. Biologic desulfurization is a well-known topic, but improvements are on way. And while doing this, let me underline, our investors or our operators should be always having a spirit of cooperation with academy, with universities, because research and developments in university will really help to this. We can report and prove these improvements, and in our laboratories, we have some pilot systems which can simulate their real-time systems. I'm out of breath. Sorry for this, but I am only 25 seconds late. I have completed it in only 15 minutes. Thank you very much. If you have any questions, I can take it. Thank you, Nuri. Yes, you have completed in a very timely manner. Thank you very much for this nice presentation. I have listened to your first presentation too. And there were some questions which had been asked, and you have answered them too. Do you have any questions related to this nice presentation? Anything you want to learn? I think there is. Kadriye from TAGEM, Serdar İçok, and Kadriye have questions. And then I want to make one sentence of comment. I hope you can hear us, Nuri. Especially, we have some problems related to using the fermented methods, because with the salination effect, the plants are just burning, and we cannot use it. Is it because of using salts during H2S elimination? And what can we do in order to eliminate this problem? Thank you. Thank you. Salts, maybe instead of salts, we can use conductivity. All ionic materials enhances conductivity. But the real salinity is related to the bit saline water. If it's not coming from the underground water, we are not expecting salt as high as to burn the plants. If there is a problem because of salinity, the easiest method is to add water in order to decrease this salt per hectare. Diluting is the best method. But the reverse osmosis membrane systems, and we have a few completed projects to use water again and again, not to discharge it. Membranes are very successful, especially in reverse osmosis. But finally, in Turkey, in recent storage processes, it's going better. According to regulation, there was only 1 month storing, but in EU applications, it was between 5 months to 1 year for storing the wet part. And also I spoke of the dry fermentation. When we go to the dry fermentation, there is an important decrease in the volume of the wet parts. I hope it helps. Thank you. Gadianum asked this question as a part of the project which we are running. These are important. Of course, we are using this scientifically. I can share it with you if you want. Yeah, thank you very much. I think Serdar raised his hand. Yes, thank you very much. My question is related to the following. There is a 15 kilowatt system. There's a 20% methane increase. Can you elaborate on the system? It's an ultrasonic system. Ultrasonic sonication is based on the sound waves. There are some hats which you didn't see in the panels. They are crossed. You give a sonication energy. It has around a 30-second reaction time. When it is put to the output part of the circle, since it's a biomass too, and since it includes minerals and enzymes, you are blowing them out, and then you can decrease it when you enter raw material, and up to 20% there might be gas increases. It's just blasting with sonication. Thank you. And this is a system which is patented and used in Europe. If you want to have more information, we can help you. Thank you, Serdar Bey, for your contribution and question, and for your answers. And Eşil has a question over the chat. I think later on you can answer her. I cannot see it, unfortunately. What do you think about using the poultry waste with the dry anaerobic digestion method, and what are the innovative approaches to decrease pH effect? We know the problem with the poultry waste. It has a lot of ammoniac or nitrogen in it. Especially free ammonia can create toxicity. It's suggested that it's not suggested to use poultry waste as the substrate. It needs a 30% blending. There are solutions. It can be diluted. The ammonium can be removed from the system and then taken into the reactor. And also you can use membrane reactors, and you can eliminate selectively with ammonium phosphate. We haven't used the poultry waste in the dry fermentation because the cattle, greenhouse, and poultry waste are very high, millions of tons. You know, it's better than us. We suggest to use dry fermentation. You know, the poultry waste have a 25% dry if it's an egg poultry, but it can go to 70% if it's a broiler. So you can blend it with, mix it with the other urban waste, and you can create an excellent prescription. We have some TÜBİTAK projects, we can share it. Yes, we can discuss it because there is a business person in the Netherlands, and they had some pilot works in Marmara region, which is related to poultry fertilizer. and ammoniac was intensified, then eliminated, and even they could create an organic fertilizer. But the other companies didn't find its feasibility enough. Actually, there are examples in Europe. Since they had problems with transforming the installed system, as of now, it's not being used a lot. Thank you very much, Nuri. Sorry for being so fast. Let's share the results of the projects with us. If you get in touch with us, I will share it with you.
Thank you very much. Thank you. The second speaker is Serdar Üçok, and he will be talking about the biogas formation stages and use. The floor is yours, Serdar. If you can also briefly introduce yourself, will be appreciated. Hello, everyone. I joined this panel from Kahramanmaraş Türkçe İmam University, from the Faculty of Agriculture. Of course, I study biogas and energy, and I will talk about our study-based biogas formation stages and use. I would like to mention what is biogas, what type of wastes it consists of, and what are the application areas. Today, with the development of technology and the increasing population, the demand for energy increases. And of course, consumption also increases. So for this reason, we take energy, as you know, basically from two sources. One is fossil energy and one is renewable energy. Of course, fossil energy is used more and there is a less use of renewable energy today. And of course, due to fossil fuels, the greenhouse gas increases and this damages environment. If you look at the fossil energy resources, we have coal, oil, natural gas, uranium, lignite, and similar wastes. And the renewable natural energy resources are solar energy, wind power, hydraulic energy, geothermal, and of course biomass. And among the renewable energy resources, we have biomass energy, which has an important place in terms of being environmentally friendly, clean, and high in energy efficiency. Biogas in biomass contributes to reducing carbon dioxide emission and greenhouse effect, as well as producing, of course, a clean energy source by reducing the rate of greenhouse gases. The biogas form of biomass is extremely important, and we have also the advantage of organic fertilizer production. In our study, biogas and its formation and its use has been investigated. Let's first define what is biogas. Biogas is formed as a type of anaerobic substance degradation with 40-75% methane, 20-38% carbon dioxide, 1-2% hydrogen, and 1-2% of hydrogen sulfide. And of course, the amount of heat provided is also important, which is around 4,700 and 5,700 kilocalories. This value is equivalent to 0.62 liter of gas oil, 1.46 kilogram of wood coil, and equivalent to 4.70 kilowatt hours of electrical energy. Let's see what type of wastes are used in biogas. Basically, we can classify it in 3 categories. The first one is animal wastes, the other one is vegetable waste, and the third one is urban or industrial waste. In case of animal wastes, we see bovine, ovine, and poultry animal manure, like cattle, sheep, goat, and of course chicken, duck, and so on. Under the vegetable waste category, we have wheat, barley, rye, oats, and so on. And as for the urban and industrial waste, you have, of course, the sewage or bottom sludges, which are formed as a result of for biogas production. In biogas production, you can see what is the rate of each residue, let's say. Well, the pig manure, first of all, and cattle manure and other vegetable wastes play an important role. In Turkey, cattle manure is used quite dominantly. In case of cattle manure, as you can also see, the average gas production value is slightly less compared to other manure. Poultry or algae give a better yield or performance. For biogas facilities, of course, this average gas production value is extremely important. And if it is low, of course, it creates a disadvantage. So we can basically make different mixtures to increase this rate. For instance, you can, as we know, ammonia rate is very high in poultry manure, so it gives certain damages. So if you can combine them with algae or other types of animal manure with the co-fermentation process, you can decrease the damaging effects of the poultry manure. Let's have a look at the biogas formation. Biogas consists of stages in which the synthesis and decomposition processes of many microbial species occur. Well, of course, there are certain stages like hydrolysis and then acidogenesis, acetogenesis, and methanogenesis. These are the 4 stages of biogas formation. First of all, hydrolysis stage comes. In that part, you have the complex organic compounds, and they are broken down, which produces sugars, amino acids, or long chain fat acids. Generally, carbohydrates break down faster, and proteins or fats do slower. Looking at the wastes here, the hydrolysis stage takes a little bit long, which of course affects the gas production. That's why preliminary measurements and calculations are extremely important. Then there's the stage of acidogenesis, like different acids playing a role here, which is followed by the acetogenesis for the main product. In this part, acetone is created, and then it is broken down to create methane and carbon dioxide. The formation of methane and carbon dioxide takes in 2 stages. The carbon and hydrogen in the environment is created, and as the acid is broken down, you have higher amounts of methane. Let's now have a look at the biogas usage. Now let's have a look at the biogas usage. We know that biogas is used in heating, and it consists of methane gas present in combustion in biogas. It can be used directly. If you look at the use in energy, in biogas facilities, we see that electrical energy, it can be used directly in electrical energy by the help of the generator. It is burnt and then used as an electrical energy. There are also uses of biogas in motor vehicles, like purification. In diesel cars or in other types of cars, it can be mixed at a certain rate and used there. I think another important part of biogas is that it can be used as a fertilizer. Throughout the world, there are various studies, but of course, there are certain missing parts in application. As a result of the anaerobic fermentation, there's the biomass product, and it can be mixed with various wastes. Sometimes nitrogen amount can be high, which pollutes the soil. So there can be trials in field or in greenhouses because it is quite missing. It's a quite missing part in our country because fertilizer is being imported in our country, and this biogas is not very widely used. So I think that should be also emphasized because organic fertilizer is extremely important for our country. So the number of studies should be increased. So with the reduction of the pathogenicity, you acquire a nice set of fertilizer. And as you achieve that, you can see the rate of increase. And for the conclusion and recommendations, I can say that biogas is very important for both our country and for the world, and it holds an important place in this industry. We have to make the use more widespread, and for the country, I think it is going to be very helpful. And I also encourage other experts and researchers to study more in this area. Thank you so much for your interest. Thank you very much, Serdar. Since you started your presentation, I'm trying to understand whether one of our audience has raised her hand. I don't know if she can hear us, but I would like to thank you very much for this general comment. But there are, of course, certain areas that has to be handled, as you also mentioned. We know that your university, and we also have a research institute in your university, and together with that university, those missing parts that you have pointed out in your presentation should be handled and dealt with R&D studies in your institution, in your university, which will bring more comprehensive data set. Thank you so much for this know-how and for piling all this information. Thank you. Now, our third speaker is Ömer Eren. He will be talking about potential of biogas production from mushroom compost waste in Turkey. Ömer Eren. All right, so could you introduce yourself? Can you see my screen? Now we can see the screen. I think you can see now. My name is Ömer Eren. I join you from Hatay University. I work at the bioengineering department as a lecturer. My main topic is energy plants and also life cycle assessment. We look at how much we pollute the environment basically when we use these systems. You may ask how I decided working on the mushroom compost waste. We had a master's degree student, and in their study, we wanted to check how much waste we produce and how much water we consume. And while doing so, my eye caught the mushroom compost wastes. Of course, the thesis is different. We are going to be presenting the results in a different place, but here, I just wanted to discuss a little bit about the biggest complaint of the producers, which is mushroom compost wastes. And up to that point, I had never had any idea about the mushroom compost waste, to be honest. So I just wanted to look at the literature, what has been done for mushroom compost waste. And I also realized that, of course, some contribution could be made in this event, because the producers cannot sell them or give them back. Only some farmers could use it as a fertilizer. And of course, when it rains, these wastes or the nitrogen inside it goes into the soil, which probably pollutes the environment. So let's see how we can produce biogas from this waste. I will go very briefly. As you know, as you all know, the land use is becoming scarce all around the world, and due to these requirements, we see that the cultivated mushroom cultivation is also making a contribution there. And all around Turkey, probably you see a cultivated mushroom facility, which is a quite advantageous production area. In Turkey, if you look at 16 years, the rate of cultivated mushroom is increasing. Of course, consumption is increasing. You can see here the consumption per person in Turkey. In 2020, the number has increased quite tremendously. These are the numbers that we acquired from the state statistics authority, and but there are data for only 32 provinces of Turkey. I don't know why other provinces were not included. For instance, Hatay province was not included in this data set. And as you can see, the white mushroom is the most cultivated species. Agaricus bisporus is very commonly used. So button mushroom is used or cultivated the most in Turkey. The biggest problem here is the waste of the mushroom compost waste. This is well given in different terms in the literature, like spent mushroom substrate or spent mushroom compost or mushroom compost waste. So for each kilogram of mushroom produced, you have 5 kilogram of waste. So it's a really significant challenge for the world. So if you produce 1 kilogram of mushroom, you produce 5 kilogram of waste. What we call compost is basically composed of straw or sawdust, gypsum, mineral salts, and you produce a different waste as you use this residue. With the industrialization, we have started creating or producing a lot of waste, and we cannot make use of such waste. So the world cannot clean itself, and that creates a big trouble for us. So let's see for which purposes we can use compost waste. Well, it can be used for different purposes, like production, bioremediation, cleaning the soil from heavy metals. It can be used as a plant medication. So it can be used in different areas. You can feed animal, you can use it as organic matter, and you can also use it as biogas. I will not go too much into the biomass introduction or definition. What you see here, MCW, is the agricultural waste and one of biomass resources, especially as biogas. There are studies in literature from Europe especially. There are also studies from Iran. You can see that Perez studied 13 cultivated mushrooms for MCW. Kayar's thesis shows us the biogas amount calculated of MCW of a mushroom production plant in Hatay province. So we tried to identify the biogas potential here. In Turkey, you can see that you have the compost wastes from mushroom, and because you need to obtain yield. If you look at the Turkey's statistics, you can see that the production is around 55,000 tons in Turkey. And this data is only pertaining to only 32 provinces, which is quite surprising. And Antalya has the biggest share. But for instance, as I mentioned before, the province Hatay also has a great potential. I don't know why it is not included here. And if you check the website of the Ministry of Agriculture, the numbers are the same, so they don't have any extra information. As you may remember, we said you produce 5 kilogram of waste per 1 kilogram of mushroom produced. So from this calculation, you can easily calculate that there is around 277,000 tons of compost waste of mushroom. This is of course estimated. You can have more detailed calculations. I tried to use the equalities and the formulations, as you can see here. The methane efficiency or the yield is around 0.65. So as a result of all these calculations, as a biogas, you might have around 15 million cubic meters of biogas from this compost waste. And the highest potential is from the province of Antalya, with around 9 million cubic meters of biogas potential. For the methane presence, we can say that for Turkey, the potential is around 10 million cubic meters, and again the highest rate is in Antalya, which is followed by the province Konya and Kocaeli. And if you don't have the of course data from 81 provinces of Turkey, it is really difficult to of course get a clear picture for the country. And the installed power potential is around 11.32 megawatts. That is of course an estimation. Of course these numbers might go down or up based on the systems used. So this is my recommendation. I think that we should encourage biogas production from mushroom compost waste. We should have further studies, and because in Turkey there is a really good encouragement for producing cultivated mushroom, and we see a lot of cultivated mushroom facilities, production facilities all around Turkey. Each and every day, the number is increasing. So there is a huge potential for the compost waste. And these are the references. So these are all the information that I wanted to share. And as I was preparing, I also wanted to look at the environmental impact, but I didn't have the chance. So as you may remember, you can create an energy of up to 277,000 joules. So if you produce biogas or natural gas, then you might emit half of the coal.
Of course, if we generate it as biogas, this will be even lower. But the emission, biogas emission, is not zero. Never the renewable energy sources give zero emission. That's all from my side. If you have any question, I can answer you. And are there any questions or contributions to our professor? Apparently no. Maybe there's a question from the chat. You said that it can be used in the soils. After the materials had been turned into compost and then applying it to the soil, it can really enhance the soil and it can contribute to its richness. And also we have gypsum in it. I'm sure you have its numerical analysis too. Maybe you can share it with us too. Related to the result of the analysis, it's hard to hear the speaker. He has a internet connection apparently. There are many literature works related to this. I haven't gone into details. Especially, the poultry manure, but of course urea is added. I didn't want to go into details because it would take so long time. I think my colleagues will take this into account too. And the data is going from Ministry of Agriculture to Turkstat, TÜİK. It can be related to the provinces. Maybe I can direct you to our Kahramanmaraş Institute. They were working on mushroom too. There was a perfection center related to mushroom. And if you will be in touch with them, you can go into details. And it goes for the Yalova too. Thank you very much. Thank you very much. Emre Karatu. Emre Bey, could you introduce yourself, please? Dear participants, dear scientists, thank you very much. Let me share this with you. I think you can see it now. Dear Chairman, dear participants, first of all, let me tell you that we will be sharing a study with Professor Mustafa Sürmen. I am resident assistant Emre Kara from Aydın University. I am in the dissertation phase for my PhD. We have done a 2-year study, and I will be sharing the results of the study with you. It's related to biogas digestate doses on yield and quality of Italian ryegrass and their usage in agriculture. With the increase in the use of chemical fertilizers with nitrogen, we have pollution in the underground water and nitrates accumulation, and there are various environmental problems. In our region, there are fermentation waste coming from biogas plants, and we had focused on their agricultural use. The material which we had selected was the Italian ryegrass. It's a species cultivated by İlkadım, a cultivar. And the second material was solid biogas digestates, fermentation waste. They have 5 different doses. One is controlled, the other one is 0.5, 1.5, and 2 tons per deca. And we had applied it to the soil. And we tried to look at their change in the quality and efficiency. We received the material from FLR biogas plants. They really supported us with their materials. Italian ryegrass is easily established. It has a thin stem. It's a single year, and its quality is high. And also, it's an erosion plant. That's why we had preferred it. When we analyze the trial area, and we see that in terms of its organic content, it's low and pH is a bit high. It shows us that the fertilizer effect is very important. With this regard, when we looked at other microminerals, we could find ideal values. Solid biogas fermentation waste, when analyzed, we have seen very interesting values, especially in terms of EC. Apparently, they have normal values, and total nitrogen is 1.4, and it had a high organic content, and the results of the analysis showed this. I want to tell it more detail, but we have a limited time. That's why I'm not going into details. Let me show you our field. This is the big Meander Basin. It's a river in Western Anatolia. We had conducted the research for 2 years. When we look at the climate data, we have identified great differences with regards to precipitation. In the first year, the precipitation was in the winter, and the second year we had a different regime, and you can see it from here. Despite the fluctuations in temperatures, the values were similar. The planting and maintenance operations are shown in these photos. I will not be going into the technical details, but we had looked at the seed need for 2.5 million dekar, and 6 times 1.2 million was the plots dimensions. First, we had dispersed fertilizer, then we used the cultivator, and also we used rakes in order to mix it with the soil. It was easily soluble, so we had used this material in order to sow the seeds. And you see some pictures related to the outputs. First, we have seen that it is ventilating the soil. The solid biogas waste had allowed a much faster growth in comparison to the control group. And you see month by month, and during the harvest operations, first we took the sites, then we used with a grass cutter. We used the grass cutter to sow it. You see the plant height, stem diameter, hay yield, calcium, magnesium, raw ash ratio, raw protein ratio, and the ADF and NDF, the fiber values have been considered. And also we had looked at the relative feed value in order to see its monetary contribution. Of course, ADF, NDF was done in HEMDEF device. The raw fiber device, and then we used the crude ash burning method. Also, calcium and magnesium had been analyzed with NIRS method. It's a bit different from PBM, but with regards to feeds, the microminerals are not so important and they are not so foregrounded. That's why we had preferred this. In terms of the plant height, in the second year, we've observed an increase, but the average values and the application values were around 1.5 million dekar. The solid biogas was higher with 81 centimeters. In terms of stem diameter, there wasn't a significant, statistically significant difference. In the second year, there were some differences, but this was possibly because of plant height. In terms of hay yield, this solid biogas applications is 1.5 dekar. We have seen that it has more than 1 ton of hay yield. So it is slightly higher value in comparison with the control group. When we look at the other values, we see that it's going towards the toxic effect. Of course, the other values can have an effect which can decrease the yield. But in comparison with the control group, we see that it is increasing the fertility. In terms of calcium and magnesium, we haven't observed a statistical difference. These are generally percentage, so they are not very obvious, but especially with ICP and ppm values, there might be differences. But as I said, we especially focused on efficiency and quality. That's why we had added this. When we look at crude ash ratio, there is a certain wavering, but we don't see very big differences. ADF and NDF values, the higher are these values, the lower are the digestibility with regards to feedstock. And we see that there's a statistical difference in NDF values. So especially 1.5 ton decar, solid phase fermentation waste had a much lower NDF value, because in NDF we have hemicellulose, cellulose, and lignin. So these are decreasing the digestibility, especially because of lignin, especially in 1.5 ton decar, it's slightly lower. Finally, raw protein, crude protein ratio, crude protein yield, and relative feed value. These three concepts show us the quality and preferability of the feeds. In terms of crude protein ratio, 1.5 decar has 112.06%. In terms of crude protein yield, it's based on the relative feed value and crude protein ratio. So it is in proportion to the others, especially in 146 decar is showing the crude protein yield. In terms of relative feed value, when we look at preferability, especially 0.5 ton and 1.5 ton are more important in terms of preferences. But especially what is very important for us is here the waste coming from the biogas plants, because they are idle, they are not being used, and there are question marks related to their usage. But apparently they have an effect on increasing agricultural quality. We are not looking at this from the perspective of the higher is the better. We see that 1.5 ton will be giving us a much better result. Of course, this is a value of a single plant. Also in sorghum, in Iskenderiye, and in a part of my PhD thesis, in many plants, we had tried these parts. That's all from my side. Without taking more time, I'd like to extend my salutes and gratitude to you. Thank you very much, Emre Bey, for concluding your presentation punctually. Any question related to the results of this research? Any questions? Apparently no. Emre Bey, let me ask a question. The soil which you had used is a very good soil, to my observation. But its organic content is a bit low because of over-harvesting. But generally speaking, it's not a soil where you can find everywhere. I couldn't see the control parts, but when it is over 1.5 ton, sometimes we have different data dispersed over different ends, but at the end, you suggest 1.5 ton, and when it comes to 2 tons, it becomes to be toxic. Could you elaborate on this toxicity? Rather than toxicity, actually, it is something close to the control group. I cannot make a clear statement since we haven't done a detailed soil analysis, but maybe nitrate accumulation can be a reason, or maybe there's a saturation point. But also in other plants, we have received similar results with the same soil. I mean, it was close to the control group. We can say that it's a neutral, it doesn't have positive or negative effect. But in some data, we see some good results too. So it's very important to show the beginning analysis and the result analysis in order to show where you have come, and to describe them with the other analysis could be better. Maybe only after this the word toxicity could have been used. Thank you very much. Thank you very much. After Emre, we have Mustafa Sürmen, who will be speaking. Is he here? I think Mustafa Sürmen is not here. He's here. Yeah, he has floor now. Thank you. Hello? I couldn't see Mustafa yet. Could you turn your camera on too? Not microphone, the camera. Hello, everyone. Hello, Professor Mustafa Sürmen. Thank you very much for waiting until now. Could you please introduce yourself very briefly too? Can you see my screen? We can only see you. Now your mic is off, Professor Mustafa. Sorry for this technical delay. I am from the Agriculture Faculty of Aydın Adnan Menderes University. Since long years, I have been working in Ministry of Agriculture, in the Ministry of Food, Agriculture and Livestock, EG of Agriculture Research and Policy, namely TAGEM. That's why I'd like to thank everyone who had organized this symposium on behalf of the Black Sea Agricultural Research Institute. Also, recently, we have lost Şahin Bizlenci recently, so I'd like to commemorate him too. He was a very important lab practitioner. Distinguished chair, dear participants. Of course, since we are discussing bioenergy, biogas is a related working area. So I'd like to share with you some feedstock which we are growing. My colleague has already covered a great part of this. Still, we are going on this. What's our advantage? We have a biogas generation plant. It's a professional enterprise. It's producing intensive liquid and solid biogas waste. But as is stated in the previous presentation, there are some challenges related to using these wastes in biogas. That's why we are researching on different product groups. Under normal conditions, these are seen as alternative energy sources, but according to our observation, its effect is especially more important in terms of increasing organic matter in soil. But our study also shows some advantages, some effects of the Italian ryegrass. I will be going fast because you have already seen the material used in the previous presentation. We have developed this material. It's called İlk Adım cultivar. This is the cultivar we have used. In this study, we focused on liquid biogas digestate with 0, 1, 2, 3, 4 ton per decar. My colleague has already covered the Italian ryegrass. These trials had been done side by side on the same trial area, same field, 2 different trials, and their features were similar. We have analyzed the liquid biogas. Organic content is good. Organic matter is good. Nitrogen level is good. In terms of salinity, there was a question. It's around 2.16 millimole. That's why we haven't experienced a serious problem. The species which we are using are more tolerant to salinity, and Italian ryegrass is like this. We have taken climate data, but let me emphasize something here. The wheat-like feedstock stops growing after 35 Celsius degree, and they are depressed. Aydın is a city where we observe high temperatures, especially in July and August. We are measuring the highest temperature values in Turkey, and high temperature creates a stress over the plants. Normally, if we had grown this material in Samsun and Izmir, we could take 3 harvests a year, but in Aydın it's only 2. But despite we can do only 2 harvests, they are still satisfactory. We did 3 replications, 6 times 1.2, which makes 7.2 square meter plots, randomized block design. Sowing date was November in 2016 and 17. We had done harvesting, cutting 2 times, and sowing norm was 2.5 kilogram per decar ryegrass seeds. You see the structure of the trial, liquid biogas usage, sowing, the first growing, the other ones, and harvest operations. We had left a certain plant height and then cut it. You see the last situation. You see the plant height, stem diameter, high yield, calcium magnesium ratios, and crude ash ratios, as it was presented in the previous trial. Crude protein ratio, protein yields, ADF, NDF, and other features, some chemical, some physical, had been studied. Also digestible dry matter, relative feed value, and other parameters were calculated based on this formula. If you look at data, plant height and stem diameter, and you see the unified statistical analysis over years, we couldn't find a significant change. Only there was a difference in stem diameter based on years. But the most important parameter for us is the hay yield, and there is an obvious increase here. If you have done regression analysis, as the chairperson, the issue dwelled upon by the chairperson could have been observed. But when we look at it, based on the dose increase, I think the design of the trial proves itself. From 1 ton to 4 ton, in 3 ton, we have the curve which allows us to make a concrete suggestion. The hay yield is much higher in comparison with control. In calcium and magnesium, we haven't found out statistical differences, neither in the crude-ash ratio. The parameters important for us, the digestibility of the feed, ADF and NDF parameters. Here, in NDF value, we had implemented 3 ton deca, the lowest MDF value. It's the value which we wanted in terms of digestibility. And we look at the crude protein ratio, crude protein percentage, and relative feed value. We have found significant statistical differences over years, and crude protein yield and relative in crude protein ratio, we had received the highest ratio in 3 ton. And we can see the differences very obviously. Taking into account the NDF values, 3 ton deca had given the highest relative feed value. In conclusion, the increasing use of chemical fertilizers causes irreversible damage to our lands and waters every year. It's a part of our pattern. It's important in local and national species because it's becoming harder to get raw material from abroad, and ilk adım cultivar was very hopeful.
These studies show that it was observed that the effects of liquid biogas digestate on yield and quality were positive. As pointed out before, previously, of course, we have to discuss how much this is going to contribute and how much awareness will be created. So, of course, an extra effort is needed. But something also took our attention, that the soil factor should be eliminated. Thank you so much for your attention. I had to go a little bit fast. Material and method is the same, so I just don't want to keep you more at this graveyard shift. Thank you so much. We would like to thank you so much, dear Mustafa. I don't know when your department separated from Black Sea Region Research Institute, so probably we have not met before, but it's great to see you. All right. Is there any contribution or any comment on Professor Dr. Mustafa's presentation? Hussein Akyol from TAGAM appreciates and acknowledges your research. Thank you very much. Thank you. And I would like to thank you for the organization. And he's also a very handsome guy. Okay. All right. I just want to make a comment about the ryegrass. Could not grasp the methodological values, but how much water is needed? That's my first question. And what is the data against about the tolerance against salinity? Well, as you probably know, in winter there is lots of precipitation until May. But although uh, this grass can be used throughout the year, of course, the water consumption potential is extremely high in summer months. And when, of course, precipitation is low in summer, of course, they need a lot of water. So if you want to have higher yield, of course, you have to irrigate them more. But during our trials, unfortunately, we could not decrease the effect of high temperature in summer months. So in the province of Aydın, which is in the Aegean region of Turkey, they grow Italian ryegrass in winter. Then they either have seeds propagated in summer by adding some grass, and then they have its self propagation in autumn. But there is also another method to have another grass, or for instance corn instead of ryegrass. So they have this type of cycle throughout the year, and that was our main study area with my colleague for the foliage, and it also yielded really nice results, to be honest. So for roughage we used this method. As you mentioned, yes, in summer months there is a high demand of water from ryegrass. All right, thank you so much. Thank you so much for your contribution. And I just want to make another comment that the systems and the processes in Turkish facilities, as you know, are being researched and studied by TAGAM, which is the agricultural department from the ministry. And so our Directorate General has certain trials and researches so that these can be utilized according to Turkish regulations. And with the help of that research, I'm pretty sure that your study will also contribute to this area, and we will of course ask for your help. Well, our objective is to be useful for Turkish farmers, so we can give you any kind of support that you need so that we help Turkish farmers and growers. And for salinity, I want to add something. As you know, for cool climate species like wheat, if you talk about tolerance or resistance to diseases, that's a quite assertive term. So we can say, yes, this is included in the semi resistant group, let's say. So it's going to be an alternative for barley, probably. It has started so. But salinity is not a very important challenge for us right now. Yes, indeed, this plant, of course, has, of course, a relation with water. So in respect of resistance to salinity and as a benefit for checking the erosion in the soil, it of course has important roles. It also has a crucial role in the production of milk for the cattle, so it is used quite widely by the growers as a forage plant. We have 25 minutes left. Now Mehmet Emin Bilgili will take the floor. Distinguished chairperson, thank you so much. Can you hear us? I can both see you and hear you. And although I know you personally, you can introduce yourself. My name is Mehmet Emin Bilgili. I work at the Eastern Mediterranean Research Institute, and I work especially on the biomass sources. And I have found a lot of benefit from the presentations that have been made since the morning. So I just want to thank all the participants one by one. When we first started, all these studies, activities like 15 years ago, people were completely unaware of what we were doing. But today we can see that all around the world, similar studies and actions are being taken. So with your permission, I would like to start my presentation. Can you hear me, by the way? Yes, yes, we can hear you. And the time is quite limited. So we need a faster presentation. Thank you. The subject of our study was the estimated on gains by the use of biofertilizers instead of chemical fertilizers in Turkey, to see how much we can benefit from biofertilizers. So that's the main topic of our study, and I want to share the conclusions, the results. As you all know, there are numerous wastes, and these are used all around the world. We have only one, which is the animal manure, that is the main topic of this study. We checked the 20 years data, and we wanted to see the electrical energy or some other parameters that I would like to also mention briefly. As you can see in the presentation, in the last 20 years, the agricultural fields are decreasing. However, there is of course an increasing population and demand for food. That's why energy consumption and chemical fertilizer use are increasing, which of course contribute to carbon dioxide emissions and of course import and financial constraints in the production process, in addition to many other challenges. As we heard from today's presentation, as you can see, the primary energy sources used to be imported by around three-fourths of the whole energy demand of the country. But today we also utilize solar power or hydroelectric and of course biomass and waste. Use of the agricultural wastes also help us replace them with other polluting energy sources, and it also helps us preserve a lot of natural sources. So we have to be very careful in the usage. As you mentioned before, biogas is used quite widely in different areas. Those biomass is used for obtaining very valuable energy source. In this study, we obtained data from the Ministry of Agriculture and Forestry, Turkey's Statistical Institute, Turkstat, and Biomass Energy Potential Atlas. Those calculations were made in 3 stages. As a result of this evaluation, first of all, in the first stage, we looked at the agricultural areas used in the long term. Secondly, we also checked the amount of fertilizer. And thirdly, we looked at the electrical energy utilized. In the second stage, we first of all identified the animal manure, the amount of fertilizer, and as a third stage, we look at the technical biogas amount that can be obtained from cattle manure, and of course the energy that can be obtained from biogas, how much electrical energy can be obtained as a result of burning. And in the first column, you can see we checked the data from the last 20 years. And the data set that we have at hand is the agricultural areas, chemical fertilizer consumption, and in the other parts, we also checked the cattle, number of cattle, and the biofertilizer production from biogas based on tons per year. And of course, we looked at the substitute fertilizer earnings in import. We checked the percentage of the substitute fertilizer earnings each year. And then we checked the approximate biogas amount that can be obtained from animal manure. And of course, we checked finally the energy recovery based on each year. Equations 1 to 7 were used to calculate, and of course, you probably know, all of you know very well the equations, so I don't want to repeat them again. In Turkey, as you know, as the animal are collected in shelters altogether, so this manure is quite accessible. because it is quite different from other herds of like sheep or goat. So cattle manure is quite accessible. So we calculate the amount using these equations that you see on the screen, and we try to see the total amount of collectible, for instance, manure, and we do other types of equations. Compared to previous studies, we try to see how much energy equivalence these have and how much electrical energy can be obtained by burning them. In addition to that, we also wanted to check for instance, nitrogen could be obtained up to 4.56 kilogram per ton in previously, and also 1.63 kilogram per ton p-values. So based on all this information, using all these equations, we calculated, and when we look at the averages, we were able to see how much substitute fertilizer we could obtain. So apart from nitrogen, there's also the organic material composition of the agricultural fields in Turkey is really poor. So rather than polluting the environment, these can be used in beneficial areas. It has been stated that 33 cubic meters of biogas can be obtained from 1 ton of cattle manure, and the electricity equivalent of 1 cubic meter of biogas was also shown in the previous slide. The fertilizer, biogas, and other energy quantities that can be obtained per year were also shown, as you can see on the slide. But of course, animal husbandry does not only give us these waste, but in the process of the COVID-19 crisis, it is really crucial to make structural decisions for industries that provide strong and durable food in the immune system of humans. So there is also an important amount of manure that can be obtained. So as I try to explain, the nitrogen and phosphorus amount is really crucial within the animal manure. These can be used for heating, for lighting, for other electrical uses. But of course, there is also nitrogen and phosphorus that come from the nutrition of those animals, and which should be excreted as feces, and of course it pollutes the environment. So that's why we can see that all around the world, animal husbandry is being moved outside the cities. And well, of course, maybe nitrogen can be considered as a pollutant, but their use in an awareness, it will of course help us combat many challenges. And this period is around 10 years for phosphorus and 5 years for potassium. And also, there are also quantities that we have um, identified, and we can share, by the way, all this information with participants if they would like to see. Unfortunately, this is the amount of chemical fertilizer being used in Turkey, and the red one, the red circle, is the one that is being imported. So if we can substitute it by 40%, it is going to be a huge solution for environmental pollution problem. So we can collect all this manure from animal shelters and use them as a source. And we also estimated the biogas has the potential to use 5% of the annual energy consumption in Turkey, which will increase our energy potential. So that's the conclusion. We should use animal manure in biogas production. We can use trigeneration or cogeneration systems, which will bring us more heat and electricity power. So, as I mentioned before, in this study, we used the data from the last 20 years of the Ministry of Agriculture, Forestry, Turkstat, and BEPA. And these are our findings. It is estimated that 40% of chemical fertilizer is imported. An average of 20% of this amount can be substituted with biofertilizers. So that's a very big amount. And we also estimate that the biogas has the potential to use 5% of the annual energy consumption in Turkey. So it can be basically recovered. So thank you so much for your attention. And of course, I'm open to your questions and comments if you would like to contribute. Thank you. All right. Emin, thank you so much for this descriptive and comprehensive study together with your colleagues. Is there anyone that would like to contribute to this nice talk? I think there is no comment or question right now, but I just want to add something to his presentation. Looking at the results, I think you mean you have manure on the one side and energy on the other side. When the biogas facilities are established, of course, their main drive is to produce electricity, and but unfortunately, they always go towards creating energy. But in time, we see that the for utilization of wastes as a biogas source, as an input, and also as an output, should be basically the main drive of this area. And the numbers also show that. So these can all be used in this area. So I just wanted to make this comment, and your study is really great. Thank you very much, Emin, for your contribution. Thank you. Thank you very much. But if there is any question in the chat box, you can also answer. So finally, I would like to give the floor to Özgür Doğan if he is here. Özgür Doğan. Yes, yes, I'm here, dear chairperson. Yes, I hear you, dear Özgür, and the floor is yours. So please introduce yourself briefly, dear Özgür. Thank you. Can you see? Thank you very much. I have worked at TÜBİTAK NAM for many years, and there are 8 other institutes, of course, under TÜBİTAK, like Energy Institute, Genetic Engineering and Biotechnology, Food, Chemical Technology, Polar Research, Material Institute, Earth and Marine Sciences, Environment and Cleaner Production Institute. In recent years, we started working on the treatment sludge, and there are really good advantages and improvements. So I will try to show you and explain you what we have done. As pointed out before, we can make use of the energy of masses, biomasses, and of course we can contribute to countries' economy. That is basically our intention, and we would like to combine it with certain strategies. So we concentrate on wastewater treatment sludge, and the amount of wastewater treatment sludge is increasing lately, and more than 90% of our population now is subject to this sludge, and we see that there is around 60 gram per person per day sludge ratio. Also, the amount of treatment sludge is around 4,320 tons per day as a dry matter. So if you combine all these numbers, I can say that as a dry matter, you have around 4,000 tons of dry matter per day. And our target is to declassify this as a waste and utilize it for useful purposes. And one of the most convenient methods is anaerobic processes to turn it into biogas, and following that to make use of the heat and electrical energy. And beyond that, there are also various applications in the country, but the ideal one is to turn it into biogas and use it as an electrical energy source. As you convert it into biogas, you also have other useful substances thanks to the anaerobic process. The liquid and the solid part will be quite useful. But of course, there are barriers. We know that. Especially, you can categorize this sludge as primary sludge and secondary sludge. Primary sludge is the mud that comes to the treatment plant within the water. And that sludge can be broken down much easily. However, the secondary sludge is the output of the treatment facility with bioorganisms. So that's why it's quite difficult to be broken down and turned into a biogas. But they are converted into biogas in the same way. So there is, of course, some problem of synchronization. So if we can change that synchronization problem, then it will be better to have the biogas in a much easier way. The breaking down process of the secondary sludge is around 30%, but for the primary one, it is around 60%. So eliminate this difference. As pointed out before in the previous presentations, we can have a pre-treatment, of course, for the disintegration to increase or accelerate the disintegration time. So we defend the idea that there should be pre-treatments, which will be followed by anaerobic digestion. And with the increase of this part, then you will have a post-treatment, which will create a biofertilizer. And these are the actions that we will take. First of all, in order to accelerate disintegration, we have developed a reactor, a hybrid cavitation reactor, on the scale of a laboratory and also on the field. So we have had certain trials, and in this study we can see that the synchronization problem, which is caused by the secondary sludge, can be mechanically compensated with a venturing system, with a pressurization system. And in this way, disintegration will be accelerated. Indeed, you can see examples of such reactor all around the world. But we also wanted to add another important source. That was the innovative part, basically, because we use sound waves to break down the cell walls, and also dynamic cavitation effect was also utilized. So hydrolysis is increased in this way, and the point is accelerated in this way.
In the studies which we have done in laboratory, you will see on the graphic, if we haven't used cavitation, the biodegradability is around 600 milligram. We are speaking of a 200 milliliter bottle. When we used cavitation, it's 1400 or 1600, which means an enormous productivity. I am sharing the photos of the reactors. We had exhibited it with our general directors and general secretaries from the metropolitan municipalities. This was very interesting for them. And this is from manufacturing. To the bottom right, you see a field activity. And we could get around 56% biodegradability enhancement. I'm speaking of the field works. Of course, this the cubic meter given to the digester is changed on concentration, and daily biogas amounts based on sludge. This is how the studies had been conducted. So we had achieved 56% in velocity, but in amount, we could have around 20-25% increase in field. We just not looked at the biogas increase, but in addition to this, there were decrease in sludge amount around 15%, because its mass had been turned into gas, and it permeated into water. The suspended solid matter slightly increases. Of course, we have obtained a biogas increase, and fragmented sludge turned more into biogas, and we had also some cellular liquids which created some biogas too. But because of the velocity of degradation, we had a richer ammonium and phosphate in the leachate. We obtained this, we can say that we had obtained this, but in previous cases, this leachate was given back to the treatment process in order to get treated, which added an additional load to the treatment cost because it implies operational costs. Ammonium and phosphate, when coming together, magnesium, calcium, and other minerals, they could create some sediments and they could clog the pipes. So we had focused on the methods to eliminate this problem too in the same way. Let's create a sedimentation in a different place and let's use it as fertilizers. Actually, these are processes and methods used in the world. These are not our original inventions, but still it was important for us to do this in our country. That's why we are working in this vein. Again, related to this study, we have some laboratory works. The ammonium and phosphate in the sludge, when added ammonium, it's crystallized, as you see on the photo. Actually, this is a very easy process. The biggest problem here is, of course, magnesium implies an additional cost, but in the plant which we were working, it had already have a higher magnesium, so we had only phosphate as a limiting parameter, but in the world, generally magnesium is the limiting parameter because it's close, our treatment plant is close to the sea, so seawater is coming. It's coming from 40 kilometers below the sea level. It's below the sea level. That's why sometimes we are having some seawater blending. So we don't need to add magnesium. We can use the phosphate in the process and we can use this strovites. And it has ammonium and magnesium as the nitrogen source and also phosphate for source. Some photos from our studies, electron microscope, some XRD examples. In this structure, we have hardness value around 90 or 90%. Generally, it's over 90%. Sometimes it can go up to 99%. We said that strovite had been sedimented. It had a fertilizer value. Can we use it directly? Of course, there will be some restrictions. We have some regulations too. Organic, mineral, and microbial fertilizers regulations exist. There are some limitations in terms of heavy metals. We had looked at the regulations to nickel, lead, zinc, mercury, chrome, and tin elements had been studied. These are the values required by the regulations, and this is below the limit values. We had done some pathogenic works in order to identify its pathogen content. The last two examples are from our samples. We haven't found any pathogens, and to the right we have stable raw sludge, crude sludge, had not been treated at all. It doesn't have pathogen either, but there is a soil bacillus formation, an anaerobic microorganism. It's a pollutant, but it's not in the pathogen class. But the studies related to pathogen is something required by the regulations, but we should go beyond the regulations. We have contacted TAGIAM, and we have nice thoughts with them in order to clarify. We have some other parameters. We cannot only limit to the to the pathogens. Also, there are microorganic pollutants, hydrocarbons, PCBs, other endocrine deteriorating chemicals, micropollutants coming from the drugs, medicines, and microplastics, which is a very important parameter for us in TAGEM. We looked at them, and of course we will continue our studies on their effect. In conclusion, we had understood the characteristics of the sludge and its characteristics. Features of the liquid gas, biogas increase, ammonium and phosphate increases. All this information could be obtained as a result of these studies, but of course, we will continue to study, and TAGEM has assumed important roles and will assume important roles in field trials. Thank you very much. I think I have a few minutes more. Not only with treatment sludge, but also, as was discussed in the morning session, it's important to use these results in biogas plants where we are using animal waste and also the kitchen wastes. It's possible to benefit from their energy in this way, and the remainder can be post-processed rather than pre-processing. We can benefit from their solid features and also liquid features and also solid features if they are solid. According to us, any kind of waste can be used as a part of this if we can increase its biological features, and especially animal wastes, urban wastes, municipal wastes coming from kitchens, and treatment plant sludge can be used in priority. Thank you very much. We are running out of time. If there are any questions, I will happily answer them. We are already behind the schedule. Thank you very much, Özgür Bey. I'm so glad to have listened to you again. We were supposed to finalize around 5:30, and it's 5:45. We already had a half an hour delay for the second session. I don't know if there are any questions or contributions. So far, I haven't seen any questions, but it's really hard to be the one who makes the final presentation on a program. It was a nice presentation. We are in touch with you. I believe that your body of knowledge, the body of knowledge existing in research institutes, especially with regards to field activities, and turning them into, translating them into regulations, are important topics, especially evaluating the treatment sludge is discussed a lot since 20 or 30 years ago. It's discussed a lot, and it's being disposed of first in the soil, but it's important them to have a contribution with regards to plants' health and productivity. If we can do this, maybe we can eliminate this problem from the roots. Thank you very much, Özgür Bey. And Hüseyin Bey is looking at me and asking me for adjourning the session. I'd like to thank all participants, representatives from universities, dear researchers from TÜBİTAK, and distinguished researchers from TAGEM. Thank you very much for the presentation you've made, contributions you have made. See you tomorrow to listen to other colleagues. Thank you very much. Have a nice evening. Tomorrow, third session will be beginning at 9 a.m.